Okay. Hello again, folks. Probably, possibly for the last time. Not to be dreary. I did that twice now that I've said that to my students, and I feel bad about it. But let's carry on. Anyhow, today I'm just going to go over the solutions to the file that I had mailed to you, or linked to you at least. And it looks like this, of course. And there's 52 problems. As I had explained, the first 20 are from the first test that I had made way back in, when was it, February probably. Anyhow, I'll go through the whole thing, but I'll start with that. And then we'll get into the new stuff. The 32 questions that follow are basically stuff that you hadn't been tested on yet. And I tried to make tables and such to make it easy to get through. If you're working on this now, and that's fine, maybe have some formulas and stuff at the ready. Anyhow, where did I put my glasses? Yeah. What is there? Okay. Oh, there you are. Welcome to my hallway. Okay. All right. Let's see. The first question is about inductive reasoning. Just to summarize, let me see if this writes. I should test this. Yes, yay, good, right. Basically, there's two types of reasoning, at least outlined: inductive and deductive. When you think inductive, right, as far as the goal is concerned, the goal is to basically form a general conclusion, right, or perhaps you might say a theory or a rule, something like that, from the observation of specific experiments, specific examples, observations, etc. Okay. This is basically how, as an example, scientific method works. You start with some phenomenon that you observe, some specific example of something, and then through hypothesis testing, I'm not go into that, but you try to form some kind of a rule, right? That is a general rule that can be applied. And that's really what this question is about. Just for the sake of comparison though, there is deductive reasoning, and in that context I would say the goal is to form a specific conclusion this is visible. It's kind of faint. I gotta dig out the duds. And remember not to pick them up, because I always do that. Put this back here. For deductive reasoning, I'm sorry, maintain focus here. It's to form a general, the goal is to form a specific conclusion from a general statement. A rule, or a theory, or something of the like. What this most closely resembles is, I would say, proofs in geometry. If you've ever taken high school geometry, you know that often you are asked to prove a relationship between two things, or to say that something is a certain angle given some rules that you are handed. Anyhow, this is more what math people are inclined to do. This is more what scientists are inclined to do, you might say, but not exclusively. All right. As a matter of fact, the question that you had on hand is something that would require inductive reasoning, because you're given specific examples and you analyze some symmetry between them, and then you try to formulate a general rule. Anyhow, not to belabor the point, but here's what it looked like. Wish I had more board space. Oh, brother. I have to turn the light on so it's getting gray again. The actual problem looked like this. Six times 1 times 2 times 1 is equal to 12. And then beneath that you see 6 times 1, pardon me, 10 times 2 times 2 is equal to 240. And then 6 times 100 times 2 times 3 is equal to 3,600. Now, if you had more time, you might try to formulate sort of a model, all right, based upon these changes. But even if you didn't go that route, you could still figure out what the next line would be, all right? Analyze what is the same here, all right? 6, all right? What is different here? You have powers of 10 in this case, all right, that they're written as the actual product. This is 10 to the 0, 10 to the first, 10 squared. The next one will be 10 to the third, which is the same as 1,000. And then here, look for the symmetry again, all right? What is the same? These are all 2's. So one would anticipate another 2, whereas these are increments of 1, 1, 2, 3, the next one would logically be 4. And then on the end here, you have basically the products of 12, and then a variation in the amount of zeros, all right? Again, not thinking about it too specifically, all right? Just recognizing from multiplication tables of 12, 12 times 1, 12 times 2, 12 times 3, you would anticipate 12 times 4 perhaps, and that would be 48. And then if you go from 1 0 to 2 zeros, it would be logical that this would be 3 zeros, right? Which is choice D. Okay. All right, so 6 times 1,000 times the quantity 2 times 4 is equal to 48,000. All right, which is choice D. I saw a nice example somewhere, and although it's a little bit funny, I kind of liked it. They said when you think inductive reasoning, all right, that you should think, Sherlock Holmes. All right. And I haven't read much Sir Arthur Conan Doyle, but Sherlock Holmes was authored by Arthur Conan Doyle, so it would really be more appropriate to say, don't think the character, think the person who created the character. Nonetheless, this is what I've seen. And this was a meme, basically, that I came across. When you think deductive reasoning, think Aristotle. The ancient Greeks were particularly fond of geometry. Anyhow, moving on. Let's see. Let me erase this. Oh, this erases nicely today. Okay. I cleaned my eraser finally. Let's see. Good. Yes, that definitely helps. Perhaps I should do that all the time. I don't like my board to get too wet, because that makes it hard to write on. Okay. That's better. Next thing is an example of, specific patterns. You see in the case of number 2, looks like you start out with a circle, and then the next figure is the circle enclosed within a square. It's like a very sad piece of cheese. All right, has one hole as opposed to 2 holes, or 3, or more. And then the next figure you see a circle encapsulating this same square, which is enclosing that same hole. So if you were going to predict a 4th figure or sequence of figures in the pattern, I hurt myself on that. It's just one inside the other, inside the other, inside the other. So circle, square, outermost circle, I would anticipate a very large square, then the circle inside that, then another square, and then the original circle. All right. So this would be choice D as well. All right. Okay. Now we'll get into more practical stuff. All right. Estimating. All right. Remember, if somebody asks you to estimate, this process of estimating is that you basically round first to some specific place, and if nobody tells you to do it to the 10th place, the 100th place, the 1000th place, perhaps some specific place value, then you decide for yourself what is convenient, right? But in general, it is to round first and then actually add or subtract, multiply or divide in that order. Right? So in the case of 3, you have something like this. You have, it's sort of written out horizontally. I'm going to do what I think is more practical, which is to sort of stack. So if you have, the first figure is 838, and hopefully that's visible. Okay. And then underneath that would be 566, 967, 791, and 486. As long as I'm just adding in this case, I would not stack numbers like this. If I was subtracting 3 things at once, you'd get in trouble if you're not too careful. Right? It's more trouble than it's worth. But if you're just adding, stacking things like so would be practical. And again, not to belabor the point, but as I've mentioned to you guys in the past, if you go into the field of elementary education, do the one thing that unfortunately no one seems to do, right? Give the children graph paper, right? Because I feel that for the same reason that it is appropriate when you're teaching children how to write or form letters, whatever language, that they have special paper for that, then when it comes to math, especially, elementary math that is simple adding or subtracting, having graph paper, however cuckoo it may seem, right, would teach the children to be organized. It may seem a little anal retentive, but when you add or subtract, all of the place values have to be aligned anyhow, and neatness helps. So your bosses will probably never go, here's some graph paper, but you know what? Give the children the thing that they need. Give them the tool. All right? Not to make a speech. Anyhow, round these. All right? If it is specifying that you should round to the 100th place, the 100th place is where the 8 is, right? And you make a determination based upon the number immediately adjacent to the right. If this digit is lower than 5, that is 4 or lower, right, then you would round to maybe 800. Same thing, rounding to the hundreds, decide based upon what's in the tenths, right? If this figure is 5 or greater, and it would be, then you would round up, in which case it would be 600. If this is 6 again, and you would therefore change this to 1 digit higher, just realize that that's going to encroach upon the thousands place. Because you would end up with a 2-digit wide number, you can't fit it into one block. Again, graph paper would help a person illustrate that point, all right? You can't fit 2 digits into one box. At least you shouldn't, all right? All right. This is greater than 5, or 5 or greater, because it's 9. So this will change to 8. It would be appropriate to line it up like so. And then the last one, this is a 4, sitting in the hundreds. So based upon the 8 here, you would round that to 5, right? And then just change the digits after it to zeros, okay? Anyhow, at least if you're doing this in the traditional method by hand without a calculator, all the place values are aligned appropriately, and you go through each column. Right? That's the way that we were taught, at least 20, 30 years ago. All right, zeros, all right, zeros. 14, 14 plus 8 is 22. And 22 plus 5 is 27. So you will put a 7 here and then carry the 2, and then you would have this. Every 3 spaces you put a comma insofar as the United States is concerned. That's the style here. So 3,700 would be the estimate that you would get. Remember, estimates come from rounding first, then performing the operation second, right? So that's B. Subtraction is very similar, of course. In the case of subtraction, I hope this isn't too faint. The greens are always a problem. This was problem 3. Here's problem 4 again. Even though it's given to you more or less horizontally, I would stack them vertically, at least if you're going to do it by hand. All right, so if you had 743 and you're subtracting 272, that is really faint. Here's my next dud. Okay. Try a different green. Make this a little bit darker. It doesn't write on itself very well. Okay, that's a little bit better. And here's my grid here, like so. All right. Again, we're asking in this case to round to the nearest 100 again, which would be where the 7 is sitting, where the 2 is sitting, based upon 4 being here. This is a digit of 4 or lower, so you round down, which would be 700. Let's see. And based upon 7 being here, this is 5 or greater, it's 7, you would round up. So this would be 300. And then it's just a matter of going column by column. All the place values, when you add or subtract, must be aligned. This is 400 approximately. An estimate, which is that. When it comes to multiplying, which is the 5th question, you could be a little bit more strategic. You don't have to be as consistent. Like you may have noticed that in each of these 2 problems, it was stated, oh, round them to the same places. All right. It's not that you can't deviate from that, but that's what the instructions were. Now, if you were doing multiplication, you could be a little bit more creative, because there's the mental math skill, so-called, that would be involved is counting zeros, basically. You round the figures given to you to numbers that have zeros, the round numbers, so-called, also. All right, and then you count, you just pay attention to the non-zeros when you actually multiply. All right, this is a shortcut. All right, non-zeros, you multiply, all right? Zeros, you count. All right, you may round to whatever seems practical. So in this case, I did specify, just to give you guidance, if you had 231 times 4,854, I had suggested first round this to the nearest 100, and then round this to the nearest 1,000. I guess if you wanted to be a little bit more accurate to the actual product, then you would round them both to the hundreds place. All right. But if it's just an estimate, and nobody said that you had to be, you know, that accurate, because an estimate is not really accurate. You know? You could take a little artistic license otherwise. Right. Again, I would start out by rounding as specified. All right, round to the hundreds in this case, round to the thousands in this case. And then make a judgment call based upon the number adjacent on the right side of it. So if this is 4 or lower and it's 3, then you would say that this is about 200. And if this is an 8, which is 5 or greater, then you would round this up to 5,000. All right. Now, as stated, it's the non-zeros that you actually multiply. That's a 2 and a 5, which makes 10, just coincidentally happens to have a 0 in it. And then you count the zeros in this. There's 5. 1, 2, 3, 4, 5. So what number did you actually end up with as an estimate? 1,000,000. Okay? It's a very handy shortcut for estimating, because if it's an estimate, it doesn't have to be exact. All right? There may be several correct answers, like when you're teaching and you give this sort of a problem to your students, unless you really specify, as I had, you know, the specific place, all right, that you want to round to, all right, there reasonably could be more than one correct answer for an estimate, all right. For an exact answer, there's only one answer, right? But for estimates, there may be several, right? And the only way that you could narrow it down is to be specific like I had been. Anyhow, this is a neat trick. 2 and 3 is what is in green. The digits 1, 0, 10 just comes from the product of 2 times 5, the non-zeros. Okay. Let's see, next one is division. Notice something. When I did the multiplication, because I was forming an estimate, not an exact figure, I didn't bother to write them stacked. If I had to do old-fashioned brute force multiplying, then I probably would have, all right? But for the sake of a shortcut, you don't really need it. You just need to count zeros. Okay. As for division, these were the circumstances. Estimate the answer by rounding first to the nearest 100 and second number to the nearest 1,000. So, first number round to the nearest 10,000 and the second number to the nearest 100. This is 6. Okay. This is a division problem, and this is as it's given to you. 369. Okay. If it gets too dark, I'll turn the light on, but I think it's basically okay, right? I have no way of hearing. I'm asking questions like, is it okay? I should just yell across the universe, is it okay? And people go like, yes! Flipping out here. Okay, back to work. All right. In this case, we're going to round first. So the nearest 10,000 is where the 4 is sitting. And based upon 3, you would make this 40,000. In the case of nearest 100, that would be where the 3 is sitting. And based upon the 6 here, you would make that 400. Now, here's what I would suggest is a practical measure. When you're doing division, yes, this is the colon with the line through its symbol that is traditional here in the United States. I've seen elsewhere it's just a colon. What I would do, and there's nothing wrong with that, what I would do for practical reasons is write this in more or less the rational style, something that emulates a fraction, and take the rounded figure and strategically write it underneath the dividend here, 40,000. Okay. Reason being, there's a shortcut for this as well. A shortcut for division, and that's faint. Black here, is to cross out pairs of zeros. Right. It is basically like dividing by 10 when you cross out a pair of zeros, or if you do two at once, technically 100. But without consciously, thinking about it. So if I cross this out and this out, I have something that is smaller to deal with, right? And arguably easier. Anyhow, then if you want, you could do it in a more traditional way, right? Like this. You'll get the same answer using smaller figures as if you use the bigger figures. All right, 3 goes into 4 roughly once with 1 left over. I'm doing a short division here. Is that visible? That's a 10 now if I put the little superscript here. 3 goes into 10 roughly 3 times. Oh, what am I doing? Getting distracted too easily. What numbers should I have rounded this to? Not 300. That's just making it more awful. All right. Well, based upon a 6 here, this would be 400. And that makes it even easier. So 4 goes into itself how many times? Once. 4 goes into 0 how many times? 0. 4 goes into 0 how many times? 0. And then your answer is 100. If I had rounded it to 3, first of all, that would be bad rounding, right? Because it doesn't follow our established rules for rounding, which is 5 or greater, round up, right? And if it was 4 or lower, round down, which really just means put zeros in those places. Right. Anyhow, 100 is what you should get, right? And I would, again, this is where I got sidetracked. All right, write them stacked. Like so. It makes it easier for this shortcut to cross out zeros. Okay. For 7, it says, in a shop that sells a variety of nuts, the prices of some items are as given below. If Sarah buys 2 pounds of cashews, 1 pound of walnuts, and 2 pounds of raisins, how much did she have to pay? Okay. Okay. This is an exact answer. Now, they did happen to give you these figures. Almonds, this is the rate, 450. Walnuts, this is the rate, 390. Cashews, the rate is 490. Pecans is 370. And raisins is 310. All right. No estimating in here because it was not specified. You're just going to get the exact answer. All right. This person, Sarah, all right, buys 1 pound of walnuts. No, 2 pounds of cashews, sorry. So this would be times 2. All right, and walnuts is 1 pound, so this would be times 1. And raisins is another 2 pounds. So you would have to follow the order of operations. Realize something, and again, not to belabor the point, but these are unit rates. And a unit rate basically is a conversion factor that relates money to some other sort of unit, which is usually, in this case, it's like, you know, grams or pounds or whatever have you. So what would actually happen if you were to analyze is that the units would cross cancel, right? I would put a denominator of pounds under each of these. It's really not necessary in this case, but that is really the intricacy of what's going on. 1 times 390 is simply 390. Again, I would encourage a person to write this on graph paper if they're doing it by hand. 2 times 490, you have to do the calculation, is 980. When you add or subtract, in this case it's exclusively adding, so I would do more than 2 stacked. You have to align the place values, which is why, again, the graph paper little boxes would be to your advantage. You can make sure that everything locks up nicely. 310 times 2 is 026. So this is 620. And then you just add as you normally would. All right, zeros. 2 and 8 is 10. 10 plus 9 is 19. Decimal points will line up. Carry the 1. All right. 1 and 3 is 4. 4 plus 9 is 13. 13 plus 6 is 19. So you would have $19. It would cost 90 cents. All right. Problem 8 is a proportions problem. And the trick to solving proportions is to cross multiply. Okay. Remember, to solve proportions, it's basically a fraction or something that emulates that set equal to a second fraction. And the trick to this is to cross multiply. Now, the only other thing I would have to forewarn you is to be consistent. When you are trying to decide what goes where in each of these 4 voids, if you will, I do it like this. You know, not rigidly, but as a strategy, right? What is discussed in the first sentence, I would make those the numerator and the denominator respectively. And then that will establish what the top is and what the bottom is, right? What type of unit, right? Be consistent. What you establish as being the top type of thing and what you establish as being the bottom type of thing, make sure that you conform to that in the second fraction. This will be derived from the description of the second sentence. Okay. Now in this case it says an electric pole is 16 feet high. I'll just draw a picture. And it casts a shadow. There's a happy sun here, casting its rays. And the shadow is 8.5 feet, which is definitely not drawn proportionately. Anyhow, I would establish, therefore, height, since that is just for the reason that it is discussed first, as the top, and shadow length as the denominator. All right? Just because of the way that it's discussed in the word problem. Be consistent that way. So 16 up here and 8.5 here, respectively. All right? Then in the second sentence it says, what is the length of the shadow of a 21-foot pole? All right, something taller. If height is established as the top here, do the same thing here. And then since we're looking for the shadow length, you need a variable. So use some letter, X or S or whatever, would be logical. right? And then cross multiply. Right? Multiply diagonally here. Sorry, son, you have to go away now. And then you write an equation. 16x, and then multiply this way. 8.5 times 21. If you don't like parentheses, you could use multiplication dot, but I just don't want to confuse it with the variable that I just coincidentally have chosen. Okay? All right. All right, at this point, you have an equation, right? Clean up or simplify one side before you start applying algebra, right? As a strategy, right? All right, you perform arithmetic first, right? And then you perform algebra second. And what is the difference? Well, arithmetic is sticking with one side or the other and performing the operations as they are expressed. So if it says multiply, you're multiplying. Algebra is introducing things from over the equals, and that is performing opposite operations. So what I'm getting at is just do the multiplication that you would have here, and in which case you get 178.5. And if you can't do anything with 16 and x, and you really can't because one is a number and one is a letter, all you could do is just sort of press them together. Now, to solve this, perform algebra, because you've hit a brick wall and you can't do anything else. When you move a figure over equals to combine it somehow with the other figure on the opposite side, you perform opposite operations. So if it is being multiplied here, and it is implied that they are being, divide by 16 here. That is the beauty, the zen of algebra, the gift of the subject. There's a cancellation effect because something divided by itself, with the exception of 0, is 1. Math people are notoriously lazy. Efficient would be a nicer way of saying it, but they don't write things if they don't have to. So you don't have to put 1x. More likely you would just put x, which is what you're looking for. All right? And then you can take your calculator, we do it by hand, but whatever the case may be, you get this figure. All right? 178.5 divided by 16 is 11.15625. I don't know if it's terminating, but I believe it is. And they would ask you to round to nearest whole number. I did make a note here. It said round after, not before. You are not really looking for an estimate, right? An estimate would imply that you have to round first, all right? If you're rounding after you've done the operations, it's just a rounded number, you might say. Right? Perhaps for the sake of significant figures, as in a science class. Anyhow, the whole number would be the ones place, which is where this particular one is sitting, and you would make a judgment call based upon one that is coincidentally here in the tenths place. If this is 4 or lower, and it is, then you would just round down. So this is about 11 feet. Which makes sense. You know, if you think about it, a shorter pole casts a shorter shadow. A longer pole casts a longer shadow. 16 is to 8.5, is 21 is to about 11. Now, in the case of number 9, you could do the exact same thing. You could set up a proportion equation. Or you could try conversion factors, which you would deduce from what you're reading. Here's what I'm getting at. As is often the case in math, there's more than one way to do it, is to solve a problem. In the case of number 9, it says each gallon of porch and deck paint, that's the brand, paint covers 150 square feet. right? If you want, set up another proportion, all right? And then just alternatively, you could try this, all right? Conversion, which is useful in, elsewhere. Unit conversion, especially in a chemistry class. All right? Whatever you are given, you will multiply by what is called a conversion factor. I'm just abbreviating conversion. And I'm sort of trying to imply that it is fraction-esque by putting this line here. There's a top and a bottom. And that will cause a cancellation effect, which will give you strategically what you want. All right? I'll do the same problem two ways. If we're sticking with the system of setting up a proportions equation, then again, let the first sentence basically be the first fraction. So if it's talking about some brand of paint, porch and deck paint, it covers 150 square feet. It's 1 gallon covers 150 square feet. I'm using abbreviations. It would be fine if you switched this upside down. That's the nice thing about conversion factors. It doesn't matter what the orientation is. You could, at will, flip them over. Just be consistent. If you are using a proportion and you have established in the first fraction that gallons is the unit on top, make sure to do the same thing here, no matter how it is given to you in English, right, in the second sentence. All right, so it says in the second sentence, how many gallons are needed to cover 1,500 square feet? Well, 1,500 square feet would have to be down here now because I put square feet down here. And the question of gallons is just what we're looking for. Okay, this is good to go. If you want to leave the units in place, that's fine. What will end up happening is that a lot of them will cancel. But if you don't want to dwell upon it too much, what you can do is basically ignore them, in this case, and just do the cross multiplication. Right? 150 times x is 1/2 of this equation. 1 times 1,500 is the other half of this equation. And that would reduce naturally to just this. 150x is equal to 1,500. Now again, if you can, perform some kind of arithmetic first, which is to do the operation as it is specified. So if it's a dot here, it's multiplication. Just do multiplication. It wasn't too hard in that case, it's just 1. But now, because you can't do anything else on the opposite side, what you must do is manipulate, move stuff around, specifically over equals. And when you go over equals, that's algebra, right? And it is not performing the operation given, which is multiplying. It is the opposite operation. So if it says multiply, you divide by 150, and then you divide by 150. These cancel here strategically so, and that will solve for x, because x is now isolated, it's lonely. And then you can pull the trick that was mentioned before, which is cross out a pair of zeros, right? And then it's much easier to do the actual division, right? If it's really 15 into 150, how many 15s can you squeeze into 15? 1 15, and it would subtract out completely. How many 15s could you fit in 0? 0, all right? And the answer would be 10, all right? And since it sits here, it's 10 gallons. Now, if you were to do it in the unit conversion style, which again, I like personally, it's the same thing, it's just presented in a slightly different fashion. This is very useful if you are in, say, in a physics or a chemistry class where you have a lot of units that you have to change from one to another. A conversion factor, that's its job, basically, is to relate one unit into another unit. So if it is given that 1 gallon is 150, I'll put this here in a thought balloon. 1 gallon is 150 square feet. That's what the paint covers. That is the conversion factor. And we present that in the style of a fraction. Now, I may orient it like this, or at will orient it upside down. It's reciprocal. It depends on what is given and what I would like to cancel out and what I want. If what I want is a certain number of gallons, then that means that in terms of the conversion factor, I need gallons above the line. And I need square feet to be below the line. And that would dictate if there's going to be some kind of cross cancellation effect, that square feet would be above the line here. Now, it may not be obvious why I'm doing that, but I'm going to fill in the information that I have. The question was that you were given 1,500 square feet to figure out how many gallons that would equate to. If you strategically put the unit of square feet here and the unit of square feet here, that is above the line, so to speak, and below it, there's going to be a cancellation effect in the same way that there would be a cancellation effect if you had the same number sitting here and here. All right? It would be strategic. Anyhow, let me finish filling in the numbers. 1 gallon is 150 square feet. And if I park this here, strategically so, this cancels this. And it leaves me with the thing that I want. And then it is 1,500 times 1, which is 1,500 as before. And 1 times 150 technically, which is 150 as before. And then the math would work out exactly the same way. Here. I need to get a paper towel. All right. Last of these regular sort of word problems. Missy and Carl work at different jobs. Missy earns $6 per hour and Carl earns $5 per hour. They each earn the same amount of money per week, but Carl works more hours. He works 2 more hours. How many hours a week does Carl actually work? A couple of things. This was an example from way back when I wanted you to learn how to translate something verbal into something symbolic, because that's how math works naturally, right? Right? You have numbers to deal with, and it's less verbal. All right. So if you see this fragment of the word problem, this person named Missy, and it says that she earns $6 per hour. What you ought to glean from this is the following. There is the word per in here, and per implies division somehow, like percent really means divide by 100. So this is an example of a rate, which is a glorified fraction. It has a top and it has a bottom. It's intuitive, thankfully. So if you have this number written first, $6 per would be this line for division. An hour would be 1 hour. This is a conversion factor. At the same time, there's a discussion of this other person named Carl. Right? And I'm trying not to ruin my book here. The second fragment here that is relevant is Carl earns $5 per hour. All right, a second conversion factor. So again, what you ought to glean from this is that if there's the word per, that means divide. And it's a rate, so therefore it is a glorified fraction. It has a top and a bottom, so it is 5 sitting on top of 1 hour. Do you absolutely positively need to write things like this? No, but it would help if you're feeling around in the dark and you have no clue how to go about a word problem, there is a system, which is why I'm taking the time to walk you through it. All right? Translate what little that you can. All right? It's always a good strategy. Okay. Then it says that they each earn the same amount of money per week. Alright, so already from that fragment, you could basically start to formulate something. If it's the same amount, that is a more verbose way of saying what? That they equal somehow. So we're already starting to flesh out a skeleton, if you will. An amount is referring to an amount of money. So what you might say is that, okay, the amount of money, I'm using green on purpose here, that pertains to Missy, all right, is the same, it's equal, to the amount of money that pertains to Carl. All right. Now it just so happens that how we would calculate the amount of money that they have total each is dependent upon a conversion factor. So in the case of Missy, you would put the rate of Missy, which she gets paid per hour, times the number of hours that she worked. And on this side, you would identify the rate at which Carl is paid and multiply by the number of hours that he works. All right. As anybody who works for a living knows that, especially if you're working for minimum wage, right? You get paid per hour. They don't give it to you as a fraction, perhaps on a piece of paper. But that's how it would translate in math world, right? As a conversion factor, a glorified fraction. Anyhow, they went on further to specify this. Here's a second fragment here from the same word sentence. All right. Carl works 2 hours more. All right. This is very subtle, perhaps. All right. It says that they earn the same amount of money, but Carl, because he gets paid at a lower rate, needs to work more to equal that. So what you can form from just this fragment, believe it or not, is itself a teeny tiny little equation. I know that it's bad enough, perhaps, that you have this equation to deal with, right? But it's going to be lovely, right? As long as you could identify this secondary equation, right? Which equates an amount of time, right? Comparing two people, all right? Let's start by subscribing a letter to each of these people. When we talk about Carl, let's call him K. And when we talk about Missy, let's call her M, all right? It gets, even if you start out with the most complicated equation in the world, you can whittle it down, all right? And don't feel bad if it's very verbose when you start. You will slowly whittle it down to the bare essential, to just symbols, all right? Carl is working 2 more hours. The word more is implying an operation. What does it usually imply? Adding. So it's going to be an amount of hours to start with plus 2, all right? But whose hours are they? Missy's hours, all right? We could basically describe Carl in terms of an amount of hours of Missy. Carl hours, so to speak, is Missy hours. plus 2, because he does 2 more, right? Is it wrong to have this arranged in terms of Missy rather than in terms of Carl? No, right? It just might be maybe an extra step here or there. What I'm getting at is, if I can just stop dropping things, if you want, we could do one of 2 things, right? And neither of which is wrong, right? Carl could be m plus 2. This is useful information, right? From the perspective of Carl, right? The same exact scenario, but from the perspective of Missy instead, would be this arranged differently. Missy is Carl minus 2. Okay. Now, I'm going to finally fill in, I just erased what I wanted, the formula that we have working here. Yes, there are 2. I just need the space. So to present this a little bit more neatly, which always helps. We have an amount of hours from the perspective of this person, Missy, which would be this relationship. And then, as a side note, we have an amount of hours from the perspective of Carl, which would be this relationship. K is equal to m plus 2. And you could use either one of these. It wouldn't be bad. Just have to put it in the appropriate place. All right? Then we simultaneously have the rate for Missy and the rate for Carl. In the case of Missy, we have established that it is 6/1 hour. And in the case of Carl, it's 5/1 per hour. And now, I can erase this. And I'm just going to move up the thing that I had written on the edge of my little board here. I'm going to systematically take the information here and here and here, or these 3, right? It's got to be 3 out of the 4, and stuff them in this equation that has been developed. Right? Write it like this. I got the Missy rate times Missy hours. And I'm running out of space already. Okay. Now I'm going to just write it here because I have to again. Okay. I have all the information I need. I just have to be strategic about what I'm using. Okay. If the question, and I'm just going to point to it here for a moment. The question is, how many hours a week does Carl work? That really means that I need to solve for Carl. So the variable that I end with in this equation has to be the letter K. So what I can do is, in place of Carl hours, I'll just put the letter K. But then when I'm filling in for Missy hours, I'm just putting the half of the equation here that relates Missy hours to Carl hours via subtraction. I'm just going to use the half of it, because that is just interpreting her in terms of him, All right, so it's just the letter K is the bottom line. All right, then I can fill in the two rates. All right, it's 6 over 1 hour, and it's 5 over 1 hour. Incidentally, the unit here would be hours, and the unit here would be hours. And because of this conversion factor, the hours would cancel here and here, and here and here. And the 1 would be superfluous, you wouldn't really need it. So that means that this is really 6 times K minus 2 is equal to 5 times K. And then we would perform our algebra. Right? We would use the distributive property here because we can't actually add or subtract these. So I'm going to introduce 6 to each of these things via multiplication. That's the distributive property. 6K minus 12 is equal to 5K. Make it line up a little bit nicer. I now have K's on opposite sides of this equation. What I would need to do is rearrange the parts. Let's get K's exclusively on this side. If I want to justify moving the 12, all right, I could do that via opposite operation, which means it would be pretty easy. But if I want to simultaneously scoot this 5 over to here and park it underneath the thing it most closely resembles, I'm going to do the opposite operation as well. I would just need to identify that this is a positive to begin with, and then subtract 5K. Take the letter with it, normally you wouldn't bother, I know. And put 5K here. And just because I'm running out of space, move 12 over to here. There's a cancellation effect when you have something combined with its opposite operation, that is via addition subtraction. And even though I don't know what K is yet, it's still something minus itself, so logically it would cancel here. 6 minus 5 is just 1K. And the left over here, which you could write as 1K, and the left over here would be 12. And you would have this, 1K is equal to 12. A reduced version of this, less complex, would be K is 12. Okay. That's how many hours that Carl works in order to equal Missy. Right? If you put it in here, 12, we'll put it in here, 12 minus 2, then Missy works 10 hours. So this would be 10 plus 2, and so forth. But this is really a question of Carl, not of her. Right? Right. You just have to interpret everything in terms of Carl. All right. The equations that follow are they're just one sentence, but it's an exercise in how well you can translate what is verbal into what is symbolically mathematic. I need a paper towel, so bear with me. And that's a little bit better. Let's see. These are worth translating or writing. Question 11 is twice a number. I unfortunately have to write this, because otherwise it defeats the point. Is 10 less than 3 times a number? I'm kind of squeaking that in. This is question 11. All right. This is, again, an exercise in how well you can translate grammatical English, which is problematic for math, into something that is purely math. All right. Focus on the word is. All right. If you see the word is, or perhaps the past tense, That's the equal sign. That means that all this junk on this left side of is 1/2 of an equation. And everything that follows it on this side, the right side, is the right side of the equation. This is technically an expression, a mathematical expression, and this is the second expression. It is these two things set equal that form an equation. The whole thing is an equation. Okay. Twice is a funny sort of English word because it implies both a number and an operation simultaneously. It is the number 2 and the operation multiplication. All right. If you're going to translate the phrase a number, just reduce that to a letter, a variable. So let's just go with n. You could put 2 times n, and there would be nothing wrong with that, but we're trying to make this as concise as possible, so just butt them against one another, and you have 2n equals. All right. On the opposite side, you see something kind of similar. You see 10 less than 3 times is 3, and then this phrase, a number again. So there's definitely going to be 3n at some point. What I'm sort of hesitating for is that there's this phrase, less than. When it comes to subtraction, which is what less implies in this context, remember that it is counterintuitive, right? English gets you in trouble when you're learning and teaching math, and this is an example of that. It would be intuitive to go, oh, it's 10, because that shows up in front, minus 3n. But that is wrong because it's talking about subtraction. When you see a phrase like less than, it is comparative. It's less than something, right? The something has to be written in the front. So whenever you see less than, and technically more than as well, right? It's just that in the case of more than, it involves adding, and in the case of adding, you can get away with not being strict. But less than really requires you to write this behind the thing that it's compared to. It's 10 less than 3 times. So what you should really have is 3n minus 10, right? English sucks when you're teaching math and when you're learning math, all right? It's a beautiful language, all right? I really sadly, I don't know any other language, I'm ashamed to admit, all right? But I know it for its faults, all right? And this is one of them, all right? So this is what you end up with. 2n equals 3n minus 10. And in the case of the choices, they used x's instead. So x, whichever you like. Okay, that's choice A. All right. To remind you what's going on down here. The question of variation. It says if m varies directly as p and m equals 27 when p equals 9, find m when p is 5. Let me just remind you of something. There's 4 types of variation. These are basically models of equations. So you might have the most plain is direct variation. We have inverses. Or you have joint. Or you have a combination. Think of these as basically skeletons that you have to choose from and that you could flesh out with a unique problem. So direct variation is 2 different variables, right? So let's just go with x and y. Y is equal to x, but there will be some factor in between, right? But it's just multiplying. In the case of inverses, there's a y and there's an x again, but the x is a denominator. There's a conversion factor, but it's a dividend in this case. Okay, rather than on the same tier, the variable x is underneath the factor. K is a constant, unique to the problem, whatever it is. And it's called a proportionality constant. Okay. In the case of joint, it might be something like this. Y is equal to, there's an x involved here, but there'll be the constant K, and then there'll be some other factor, which I'll just put in green here, which would be a third factor, Z. Right. They are nonetheless all being multiplied. They're all on the same tier, you might say, no fraction. Right. When you have combined, it's multiplication and division simultaneously. Okay. Bear with me in a second, I just want to verify something. Okay. All right. Anyhow, the problem that you are given, taking this into consideration, is purposely nebulous. It's purposely confusing, which I don't believe in, quite frankly. Especially when you're teaching little children. Yeah, you want to challenge them, but you don't want to turn them off either, right? So just convince them when you're teaching them something that, listen, there's definitely an answer to the question, and it's not a trick question. And then after they get comfortable with the material, then you go, yeah, okay, here, I'll give you something a little bit more challenging, and it'll cause you to think. You'll be interested at that point. Anyhow, these are your choices, right? And in the context of problem 12, it says this, unfortunately I have to write it. It says M varies directly as P. Right? And then it goes on to say that M equals 27 when P equals 9. And then it says finally find M when P is 5. Couple of things. Let's decide which of these models we're going to go with. If it says directly, we're doing this. We're just going to change up the variables so that it doesn't use x's and y's in the model. We'll use m's and p's apparently. To say that m varies directly as p is to basically do this. To put an m here and a p here. And if we take the information that they've given, blue, which is the next line here, and fill in the void, put 27 here and 9 here, still noting that there is the proportionality constant in the way. If you have the majority of information, in this case it has 3 distinct parts, factors here and the number here. If you have the majority of information, you can solve this equation, even though it hasn't been explicitly asked of you, to figure out what k is, right? Now, we're going to have to do that because the next thing is find m, they don't tell you what it is, when p is 5. Well, if we have decided that this is what the model is, and the only information we have in this case is 5, then in this case we do not have the majority of information. So we can't actually solve this. We have to go back to the vaguely considered model here and then rearrange it to solve for the proportionality constant first. How do we do that? Algebraically, right? If you can't combine these two things, then perform the opposite operation. The opposite of multiplying is dividing. Do it to both sides. It's consistently going to cancel here. Then k is equal to the outcome of 27 divided by 9. That means that the proportionality constant, based upon this description here, is 3. And therefore 3 sits in here, and therefore m is 15, which is choice B. Okay. I'm going to try to speed it up a little bit here. Those are word problems. It's worth taking the time to explain the intricacies of them, especially to a child, all right, because they are feeling around in the dark, all right? You, as the teacher, your job is to elucidate. It is not to make things nebulous, all right? So take the time. I don't care what anybody tells you, your boss or anybody else. They say, oh, you need to get done faster. Bull crap, all right? You need to take the time to explain this, to make it clear. And pardon my French, right? All right. Now, if you're writing as 13 and here's 14, you're going to write these as percents. Look at what's given to you. In this case, it's 0.873, a decimal number. In this case, you get a fraction, right? A while back, I made a handout that looks like this. I'm going to point at it now. I really shouldn't be too proud of this because it's not perfect, but there's a handout that basically describes the process here. Dots are where you start from, arrow points are where you end. And this is a system that works for these 3 styles of a number. All right, so we're going to convert these to percents. We're converting from, in the first case, a decimal to a percent. And in the second case, we're going to convert a fraction to a percent. There may be indirect paths that accomplish the same thing. All right? But here's the easiest thing, all right, in each of these cases. All right. If you were to take a decimal, all right, and you want to convert it, hold this over, from a decimal point here to a percent, you would just multiply by 100 and then attach the symbol. So, if you multiply by 100, and remember the shortcut, the effect is to move the decimal point twice. It's always twice if you're converting to a percentage. Which direction? All right? Towards the right, if it's going to a percent. So you would just scoot this over without having to, complicate things. And that would be 87.3%. right, now in the case of a fraction, perhaps I should finish even abbreviating, spelling it. It's going to be the same process because you're going to a percentage. So here, let me just look at, point at my little diagram here. If you're starting from a fraction, this end point here, and you're going to a percent, you are still doing the same thing ultimately. You're going to multiply by 100. Just realize something. If you want, you could do the same, you could accomplish the same end result indirectly. This is the most direct path. Fraction times 100. Or you could go from a fraction to a decimal first and then go to a percentage. It's up to you. In the case of converting from a fraction to a decimal, you would divide the numerator by the denominator, the top by the bottom. All right? Go this way and then this way rather than directly. So it might be in this case to your advantage to do that, and I'll do it both ways just to show you. But you only know in the long run with a lot of practice. Even now I've sort of forgotten, all right, which is more practical to me. All right, but here, let me show you. If I were to do the same thing, multiply by 100, I have a fraction, so I really would have to include this extra feature here. All right, I'd have to make this a denominator of 1. All right, and then I would employ, techniques for multiplication of fractions. 5 times 100 is 500%, over 8 times 1 would be 8. You would, because of the way that it works out, that you get an improper fraction, even still, you'd nonetheless have to straighten this out, at least to make it less complicated looking. It's not wrong, it's just not in lowest form. All right. So what you might do in that case is, as an afterthought, convert this to a decimal first. It's still a percent already. All right? And you would go, all right, 8 doesn't fit into 5, it's too small, but 8 goes into 50 6 times, which is 48, and the difference is 2. All right? 8 goes into 20, roughly twice, which is 16, and the difference is 4. If you're going with the style of a decimal, you would put a point, add a 0, drag it down, and continue. You'd end up with 62.5. There are some situations, it doesn't work in this case, where if you had a better problem, something like 1/4, you could sort of upgrade to another fraction over 100, and it would automatically be a percentage, whatever the top is in that case. But only because 4 times something directly equals 100. 25% is what 1/4 is, right? In the case of a fraction like 5/8, there's nothing that you could directly translate into 100. That would be, for lack of a better expression, a nice number, all right? You're gonna get, there's nothing times 8 that directly equals 100, that is a whole number, all right? All right, 8 times, the closest you would get would be 8 times 12 is 96, that's too short, right? And then 8 times 10, pardon me, 8 times 13 would be another 8, so you'd be overshooting it. Anyhow, this is the trick in this case. You're going to just nonetheless multiply by 100, all right? And then if you get something ugly at the end that is a fraction, just convert the fraction into a decimal. Top divided by bottom, all right? It already is at that point a percentage because you've introduced this 100. All right. Next. The problems that follow it are converting percentages to something that is purely a decimal, and a percentage that happens to be a fraction percent into something that is a decimal. Okay. All right, and what are you given? I should put this down. I need this. 15 here. 76%. 16 is 3/8%. I know that it's a little annoying, right? Or it's not confusing. You go, hey, it's like an eggplant, right? Is it an egg or a plant? It's neither of it. Well, it's a plant. Tell it to make up its mind, you know? This is a percentage, right? I know that it has, unfortunately, a number in the front that's in the style of a fraction. But if you had to say that it was one thing or the other, all right, just convince yourself. You see this symbol, it is definitely a percentage, okay? It just happens to have a fraction as part of its number that would be here, all right? Normally, the number here is a whole number, or at worst, it is a decimal number, all right? In both cases, we want to convert these purely to that, no longer a percent, and in both instances, indeed, a decimal number. So it's a little complicated, but do remember this, all right? Here's the basic strategy, all right? If you're starting with a percent, whatever style of percent it is, all right? If you're converting to a decimal, all right, you are going to divide by 100. If you are converting to a fraction, all right, you're going to divide by 100. The bottom line is, if you're starting with a percent, right, instead of multiplying by 100, right, you're going to divide by 100. If this is the end result, times. If this is the end result, divide. All right. Now, in the case of this number 76, it most closely resembles the shortcut, but in the opposite direction. All right? You're going to move the decimal point left instead. Twice left, as opposed to twice right. When you multiply by 100, you move to the right. When you divide by 100, you move to the left. To the left, to the left. All right. In the case of 76, there's a little dressing up that you have to do. Let me get a better marker. You're going to do this. You're going to do this, ultimately. But fill in the missing information. Again, unfortunately, math people, for better or worse, leave out information. All right, sometimes it's a convenience, and sometimes maybe it's just being lazy. A decimal point of a whole number would be here to start with. All right, and you would need to fill in that information if it isn't explicitly given to you. Anyhow, the effect is to move the decimal point when you divide by 100 twice to the left, without having to dwell upon it too much. So you would just scoot this over to here, and then the end result would be this, 0.76. It is no longer a percent, right? It is purely a decimal, right? Even if you had a decimal number to begin with that happened to be a percent, you would still move in that direction, left, because that's what dividing does, all right? In the case of this fraction, all right, put this aside for a moment. There's, again, possibly more than one path, one more direct than the other. Let's try it two ways. All right. You could convert this into a decimal number first. That just coincidentally happens to be a percentage. And then do that, divide by 100 as an afterthought, because it would be more akin to what is going on here. But that isn't necessarily the only way to do this. I like to go through that method only for the reason that it is a good skill to be able to convert a fraction into a decimal. So I'm going to do that first. it is the top, and I'll put this over here perhaps, 3 divided by the bottom, the numerator divided by the denominator. And since you're going to convert it to a decimal, throw in some zeros to get rolling, right? Literally, rolling, all right? 8 goes into 3, no, it's too small. Fill in the void, all right? 8 goes into 30, roughly, all right? How much? 4 would be too much. It would be 3, which would be a difference of 24, and you'd have 6, all right? Short division, long division. So this would be 60, all right? 8 goes into 60, roughly, 7 times, which is 56, the difference is 4. I'm gonna squeak it in here. 8 goes into 40, 5 times exactly. That means that this is really 0.375%. It's still a percent. It's just written in the style of a decimal, right? Again, to divide by 100 to make it purely a decimal, no longer a percentage. The effect is just simply to move the decimal point twice to the left. Make waves. So if you move it twice, you have 2 sort of waves here. It means that this, although it is really puny, is 0.00375. All right? Which is choice A in that case. Okay. Moving on. Let's see. Yeah. All right, for 17, you're going to need a formula. There's this formula we had discussed, which is percent change, how much something changes. All right. So depending upon the perspective and the context of the problem, it may be a percent increase. That is the end result, or it could be a percent decrease. Right? And how you can tell, even if they don't use either of those words in English, is if the end result is a positive, you have an increase. If the end result is a negative, then it would be a decrease. Anyhow, this is also sometimes called percent error. Right? And it is this. It's taking some new amount and subtracting an original amount and dividing by the original amount. New minus old, if you will, divided by old. And then multiplying by 100, because that makes it a percent. You're basically forming a ratio, which is what this fraction bar division symbol really would produce. And that will give you a decimal, all right? So if you then take the decimal, or if it is in the style of fraction, same difference, and then multiply by 100, you're presenting the same quantity, but in the style of a percentage, which is more user-friendly, all right? People like percentages, all right? So, in the context of this problem, it says on a biology test, a student got 19 questions correct, but did not pass. So the fact that they didn't pass is really not relevant, all right? On a second attempt, the student got 29 questions correct. What is the percent increase, right? Even if they didn't say the word increase, you could infer that again by examining what the signs would be, right? I would just take that and then fill in this formula here. It's getting a little dark, so maybe put the light on. I don't like this reflection. But anyhow, what is the new amount? 29. What was the original amount? 19, so it goes in 2 places. This difference you will figure out first. What's the difference of 29 minus 19? 10 over 19 is what you would end up with. And then if you were going to do this in the style of a fraction, you could just make 100 have a denominator of 1, right? Top times top would be an extra 0, 3 zeros. Bottom times bottom is 19. This is a percent already, but to make it a little bit more presentable, all right, divide 1,000 by 19 with your calculator potentially, and then you would get this. 52.6 something percent into infinity, or perhaps the end of your screen. Round this to a whole percent, it would be, say, something like 53%. There's an improvement because this is positive. It's an increase. If doing this exact same calculation, like the person got somehow something less, you would see that there's a negative, and that implies that it's a decrease. Okay. All right. Trying to confine myself to this much space. 18 and 19 are very similar. All right, here's 18. This is a nice thing to teach children if you want to introduce algebra to them, because it's very formulaic. All right, that if you teach them to just sort of look for, you know, key words in a sentence, is equals. All right, they can translate something verbal into something mathematical. You know, so I'm just going to write this merrily. 150% of 390 is what? To be curt, all right? Is equals of, at least to start out with, will be times, all right? If this is sitting in between them, then that's where 390 is. If this is 150%, in order to use it, you would have to use a percent, you have to convert it to either a decimal or a fraction. Right? There are some contexts in which it would be better to have a fraction, like if you were talking about simple interest formula. Because a lot of times the amounts of money that you're dealing with are round numbers, and if something is a percent, it automatically has a denominator of 100. It would make cross simplification easy. But in this case, it's just kind of in general. If you're converting again from a percentage to a decimal, you are dividing by 100. The effect is to simply scoop this over 2 spaces to the left. So this is really 1.50 times 390. All right, in which case you get 585. Is your answer. And the next one is the same process, but there's an added step. So if it says a 19, what percent of 115, I can't draw a straight line to save my life, is 1172, right? 11.72 or 11 and 72 hundredths, all right? Round to the nearest tenth of a percent, that's as an afterthought. When you have a problem like this, you can set up the sort of algebraic equation easily, but you have to sort of remind yourself, because you end up looking for a percent, you have to convert it to a percent, the result that you get. Because you're going to get either a decimal, you're going to get either, or perhaps a fraction. Anyhow, is equals of, to start out with this times, 115 is sitting here, 1172 is sitting here. For a variable, for percentage, question of what percent, I would just put a P, all right? Now, it's, instead of being pure arithmetic, because the numbers that are being multiplied are adjacent, you have numbers on opposite sides of an equation. In these cases, you always will. So what you're going to need to do is to perform algebra, which is to do the opposite operation. Justify moving 115 from here over equals. How so? Opposite of multiplying. The opposite of multiplying is dividing by 115. Strategically, it will cancel here, and you'd be left with P, right? But it's going to be the percent in the style of a decimal or a fraction, right? So if you would have entered this into your calculator, 11.72, and then divide by 115, you will end up with this. Let's see, where am I? Some terrible number. You get 0.101913, which is the correct figure. It just doesn't have, it hasn't been converted yet. right? So recognize it for what it is. It's a decimal number that you get. That is more simulating a fraction. It isn't even technically. It would be more appropriate, since there's a decimal point here, it would be more appropriate to refer to this as a ratio, because a ratio has less stricter criteria to be defined. It could be any type of number on any other. If you're going to convert this to a percentage, to answer this question, you would have to multiply by 100, remember, which means the effect would be to swoop this over twice to the right. And then if you round it to the tenths place, I believe, yep, nearest tenth of a percent, that means that you would be rounding, if this is now 10.1913, you'd be rounding where the 1 is here, right? And making a judgment call based upon 9. So this would be approximately, or about equal to 10.2%. Which is D. And here's the last from this whole test, 20. Which is a question of markup. Let me just remind you of something. In the world of percent equations, they're kind of collectively referred to as percent equations. There's three basic types. There's the type that's called part equations, the type that are called base equations, and the type that are actually looking for a percentage. And you can usually tell which type you have, even if it's not specified, based upon where the numbers are sitting in the sentence. Like if you see a question of is what, right, then you're dealing with a part. Right? It's usually a smaller number than the number given to you. If you say, if you see a question of, let's see, of what, then you're dealing with the base, which is more or less an original amount of something. And if it just clearly says what percent is, or is what percent, then you're definitely looking for the actual fraction. Okay. Anyhow, part equations are basically simple arithmetic. These two, the type that are a base and a percent equation, both of them really end up requiring you to perform algebra, which is the opposite operation of whatever is established. All right. There's different types of part equations in ordinary life. There's the type that is to calculate sales tax. But you'll notice some symmetry. It would be the original cost of something times, let me put this a little bit nicer. It would be some percentage quoted to you times the cost of something. All right. If you're talking about discount, it's the same formula, it's just subtracting that number rather than adding the number. So it would be a percent times the original cost. Right? In this case, you would add after the fact. And in this case, you would subtract. Right. Then there's these other two things. There's commission and there's markup. They are part equations as well. All right. So there'll be a percentage quoted to you in each case. Sometimes you have to look for it. That's the conversion rate. Right. They would just change the word. They would say the amount sold. Commission is like if a person works in real estate or if they work for a car dealership. Right. They're encouraged to be more aggressive in terms of selling something because they get a chunk of whatever the amount sold is. markup is basically what some store, right, like Staples or Walmart or wherever, it's like an amount of money they tack on to the cost of something that they purchased. That way they would get some kind of a profit. That's why you notice that if you buy the same calculator in two different, go to two different stores or whatever, you'll see two different prices for the exact same thing. They have different markup. The stores are trying to maximize their profits ever so slightly. All right. Anyhow, this problem is referring problem 20 to markup. So we really are going to basically use this situation, right? And it's going to normally be just two things multiplied, the percent given to us in the style of a decimal perhaps, and then whatever they originally paid for the thing. There is one little caveat here you'll see when we get to it. All right, it's a little bit more complex. The number that you end up with here ends up having to be a difference that you calculate, and it's not really explicitly stated to you. You have to sort of deduce this from reading it. All right. So let me read it now. It says a store manager paid $110, all right, for an item, right? That's the cost to them. So 110 would sit here. It's an amount of money. And set the selling price for 150, right? The markup is an amount smaller than the cost. Why? Because it's a part of the original amount, right? Usually, right? So if they're quoting $150 to you, it's not appropriate really to stick $150 here, right? Because that would be like a huge thing. I mean, you can, there's ways around that, but it would be more appropriate to basically figure out what the number that should be here is by taking this and subtracting. 150 minus 110 is the actual part, the actual amount that they've added to 110 to make something a profit for them. All right. That's the modification that you would need for this problem. So right now, this is how much we have. 150 minus 110 is equal to whatever the percent quoted to us, so perhaps that's what we're calculating, all right, times 110, all right? If you notice, if I just manipulate the equation ever so slightly, it ends up being the percent change problem, right? Because of the phraseology of the sentence, of the word problem, all right? So there's more than one way to do this is what I'm getting at. Anyhow, in place of percent, I'm just gonna put the letter P because it's intuitive, all right? And now I have this. The difference is equal to the percent that we're looking for is times 110. What is the percent markup? It would require me to divide by 110 here to cancel, and then park it under here 110. And again, this is really a disguised incarnation of percent change, all right? In which case it would be some new amount minus some old amount over the original old amount times 100. All right. So let's do the arithmetic. 150 minus 110 is just 40. This is 40 sitting on top of 110, right? That's a fraction which you could reduce. Pull tricks, right? If you have pairs of zeros, you could cross out the zeros, right, in pairs. And you're left with 4 over 11. Now, that's really what the answer is. The percent markup, right? The rate of markup here. There's another phrase for it. But it's in the style of a fraction. So, as mentioned, if you were to then convert this to a percentage, it would be like multiplying by 100, which is now 400 over 11. Convert this to a decimal would be a little bit more easy for a person to grasp. Anyhow, so you would end up with 36.36 repeating. I'll put this over here. you see this is the answer for the percentage. 36.36, the bar over the two of them. Round to the nearest whole percent would be where the 6 is. Based upon a 3 here, this is approximately 36%. Mark up. This is the correct formula, but the way that the question is asked of you is to not calculate this so much as is to calculate this. And because of that, there's more steps involved. Alright, now that was the first test as thoroughly as possible. The stuff that you see from this point onward is the stuff that you hadn't been tested on because of the coronavirus. We'll try to go through this. I'm gonna get a sip of water. I'll be right back. Okay. I'm going to translate the set from set builder notation to roster form. All right. Remember, set builder notation is this sort of alien hieroglyphics that you're given. So you see A is equal to fancy braces, and then you'll see these symbols inside. That's not too faint. It is. Okay. And here's my heads in my pile of blues that I hate. Because they either write too well or don't write well enough. Blue. You trouble, blue, you trouble. Alright. First of all, if you were going to read this in English, right, here's what this is saying. The set A, or you could say, let me do this less complex. A is, and then when you see fancy braces like this, the set, that's what this is saying when you see fancy braces, of X's. This line is read as such that, and then it describes what follows it. These are what you call the conditions. All right. X is an element of. This symbol, which is known as a lunated epsilon, is an element of, is how you would interpret that in English. All right. N is referring to, is an element of the natural numbers. The natural numbers are counting numbers. Think of your hand, right? That is the basis of all math, right? Basically our fingers, all right? 1, 2, 3, 4, 5. There are no negatives. There is no 0 with your hands. Yeah, I know you could do that, all right? But they're natural to us because they started by counting with 1, all right? 1, 2, 3, 4, 5. Into infinity, all right? And then there's a second condition here. Basically, this is saying that X is in between these two, but one of them is included. 2 is included. So to make that a little less verbal, A is the set of X's such that X is an element of the natural numbers that's stopping here, and X is, how should I say that, between or bounded. That's a little bit too fancy, I think. Bounded between 2 and 8, including 2. Right? Not including 8 because there's no equals tucked into this. It's just a less than symbol. This is less than or equals, so 2 would be included. It's a very subtle way of saying yes, 2 is what you start with. Right. Now, that is known as set builder notation. Notation being a style of writing something, right? And it does summarize basically infinity, because natural numbers, although we only count up to 10 if we have 10 fingers, right? They go on forever. So if you're then asked to put this in roster form, which sounds like Rasta, yeah. Hey, man. Okay. I'm thinking of Bob Marley suddenly. It was Rastafarian, right? Sorry. Stupid joke. All right. Start with 1. All right. Well, no, under normal circumstances you would, but in this case, what are you starting with? 2. I'm getting distracted. All right. 2 is included, and that's where you start. All right. Rather than start with 1, comma. 3, 4, 5, 6, 7, and then you would come to a screeching halt here because 8 is not included, and that would be the roster. This, I admit, is a lot less complicated than the set builder notation, but they mean the same thing. Anyhow, natural numbers, if you were to see them in general, is usually written like this: 1, 2, 3, 4, and then they put ellipses. The 3 periods, because ellipses indicate that something stretches into infinity. All right. All right. All right. 2, 3, 4, 5, 6, 7. All right, and that's basically it. All right. Not 8. Good. All right. Okay. For 22, you could draw this out, but there's actually 2 formulas. All right. Here's 22. It says determine the number of subsets and proper subsets of the following. Use formulas and or write out the possible combinations. Now, it would be impractical in the same way tree diagrams would be impractical if you had a lot of elements to deal with. But in this case, it's not too bad, and it might reinforce the concept. Here are the formulas that you would need. All right. If you're talking about subsets, just to equate you, relate these symbols. Subsets would be these symbols, like you see. Let me just validate something very quickly. Waning. What's the problem? It's making me stupider. And I'm a little obsessive too. Okay. Alright. If you're talking about a subset in general, you might see this symbol, because that, in the same way that this is an element of an epsilon, a illuminated epsilon. If you see this sort of C with an equals under it, it's referring to subsets. If you see something that is a proper subset, you would just see the C sort of symbol like that. Right? What's the difference between a subset and a proper subset? Basically, a proper subset does not look like, or does not include all elements. So it doesn't look like the thing that you started with. It is a little weird to say that a set is also a subset of itself, but that's actually true. That's why they use this symbol that has the little equals line in it, because that is in a very subtle way, it is implying that, oh, the original set itself is also one of these, right? So just a note, when you see this line, this includes the original set. Okay, now as far as formulas are concerned, subsets in general would be more of them technically, would be 2 to the n, right? Versus if you just the proper subsets, it would be 2 to the n minus 1, the 1 subtracted to account for the original you're taking out of it. What is n though? N is referred to as the cardinal number. The cardinal number is the number of elements. The contents, if you will. All right, so if you are given, this set X, Y, Z, how many contents are there? N is 3. The cardinal number is 3. That's it, right in the way of the reflection. That's still faint. N is 3. All right, so if you insert that into this formula, the number of subsets in general, including the original, would be 2 to the third, which is just that there will be 8 of them. All right. If it's 2 to the third, which is really 8 minus 1, proper subsets would be equal to 7. Okay. Now, how could you prove that? That's a little bit easier to read, right? You could physically draw it out. This is 1, a set of 3, and then there's these subsets, which are just 2 things at once. So X and Y, X and Z, and Y and Z. 3 contents, and if you use 2 at a time, there happens to be 3 sets, subsets. And then there's the situation wherein you have just 1 content each. And then, believe it or not, there is a last one, the one that is empty. I know that you might be thinking of this symbol, the null symbol. If you're going to use that, that's fine, the null symbol. But don't put it in here because it makes it look like you have a 0, all right? And it's really a no smoking sort of thing. I wouldn't bother with this in general, right? Better to just have a void, right? Anyhow, count them. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 subsets in general, right? And there are 7 proper subsets, the one that does not include all elements, all right? 1, 2, 3, 4, 5, 6, 7. Okay? for 23, it says, are these sets equal or equivalent? All right. Here's the difference between what is equal versus what is equivalent. They are synonymous, especially in English, right? Equivalent. Equal means exactly the same. All right, it means that it has the same contents. And all of them. Equivalent means it has the same cardinal number, n, and the cardinal number is just what? It's the number of elements. So in the case of 23, the first set is this, it's A, and it's called 1, 2, 3, because I wasn't too creative, all right? And then the second thing is B, and it has the names of some countries, Brazil, England, and then Japan. All right. Would you say that these are equal or equivalent? Well, they clearly do not have the same contents. The elements are different. These are numerals and these are names in some places. However, the cardinal number here is 3, and the cardinal number here is 3. There are 3 contents here and 3 contents here. So, these two are equivalent, even if that seems bizarre. If you're worried, if I had just another situation where you had the same elements but they were in some peculiar order, let's just say backwards, these would still be considered equal because the arrangement doesn't matter. Okay, they have the exact same elements, and that's all that's relevant. Okay. In the case of 24, 25, and 26, you need this diagram. So I'll replicate this. You have a Venn diagram of 2 sets, and in it there are these circles. There is a circle, it's called set A, to stylize it. And there is a second circle, which is called B. And then there are these contents. Elements would be the word that they choose to use most often. I like the word contents. If you see a U up in the corner, that's just a label. It's not a content, it's universal. E, F, and G, B, D, and H, A, and I, and then outside both of them is Q, R, and S. Question 24 is A, sort of the horseshoe shape, B. 25 is A minus B. And 26 is B, little tick mark. All right. These are abbreviations for the following concepts. When you see the upside down horseshoe, remember that this is a discussion of what the intersection is. Meaning both conditions, and sometimes the word "and" comes into play here. Intersection means, based in the context here, is the overlap only. So what's just the overlap in this case? With the two, what's the biscuit that you see there? A intersect B is BDH apparently. You can tell that just from the drawing. A and B, A minus B, is a little bit more complicated. And in that case, let me remind myself of something really quickly. I want to verify something before I go forward. I lose papers. Okay, good, because I have too many of them. Okay. This is the difference, naturally, when you see a subtraction symbol. But it really depends, the answer really depends on what is written in the front here. You would read it as this question. What is in the first, in this case it's A, that isn't also in the second? In this context, it would be B. Essentially, you're going to keep only what is in the first. Let me rephrase that because English again is problematic. Keep what is in the first only. You can, from staring at the drawing, probably figure out what it is. What is encapsulated by A only. Keep what is in the first only. But let's say that you had just a set notation given to you. It might be practical to look at it this way. The set of A, right, in roster form would look like this. It would be in alphabetical order. B, D, E, F, G, H, and I. Not I, just H. B, that's a D, E, F, G, and H. If you were to consider what is in B simultaneously, it's B, A first, let me sort it down. A, B, D, I hate the way that this writes. A, B, D, H, and I in that context. Okay. A method for going through it, if you just had this given to you rather than the picture, is to basically cross out what is in common first, which as you can see is they both have B in common. They both have D in common. And they both have H in common. And then keep what is left over in A. So what is left over in A? These three things. That means that this difference is E, F, and G. Again, if you had the Venn diagram and you read it in this context, what is in the first, that is what is in A, that isn't also in B, would be these things, E, F, G. Right. Now the last thing is this with the B with the tick mark. I'm reluctant to use green because it doesn't write very well. This is read as the complement of B, right? Which is a fancy way of saying everything that is not B. So, just over here to answer the question, I'm going to duplicate what is in B. A, B, D, H, and I is what would, to start with, be everything in B. There's English again getting me in trouble. B, 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 B. I'm sorry. My humor is lame on a regular basis. And I'm not always polite enough either. All right, the complement of B is everything that is not B. Now, we could basically dismiss out all of this stuff. Like, if I basically, it would be easier if I actually wrote, if I could basically scribble over this entirely, just not to look at it, everything that is not B is all this other stuff. Right? So that would be in alphabetical order: E, F, G, Q, R, and S. Because it includes the things that are on the outside as well. All right. Let's see. The only other symbol which I didn't include was the actual U symbol, which is the union, right? And a union would be two things merged entirely, all of their contents. The other operation that is for a different problem is cross products, which I'll show you now. Let's see. If you have this for 27, A cross B is how you would read it. This is known as a cross product. And it basically is to, what this would produce is basically coordinates, ordered pairs. As a set, right? Ordered pairs normally are what? X and Y, right? But you'll have several of them, right? So in this case, if you have A is a fruit, looks like orange, a banana, and then apple, and then B is 1 and 2, and A is written in the front of the X. How you would form the coordinates would be to do it this way. Draw arrows originating from the first thing. In this case, it happens to be A. Right? To each content of the second, which in this case happens to be B. Content. So, orange 1, that's your first ordered pair. Orange, comma, 1. Orange 2, right? That's your second ordered pair. Orange, comma, 2. Just to make it a little more distinct, now the same thing with banana. Banana 1. It's like some kind of weird what you calls it, you know, secret language, like in the military, right? They talk about alpha, beta, you know, foxtrot, whatever else. I don't know anything about it, but they, you know, to be secretive, right? It'll be like banana 1, and then banana 2, whatever that means. Banana 2. Anyhow, notice that these are originating from the element of A, the first thing. So I'm going to squeak it in here, but banana 2. Okay. And then the next thing, this is close to Granny Smith as I can get here. Apple 1. And then again, apple 2. Not to be confused with a computer. Which was a fine computer, incidentally, and I can vouch for that back in the day. An Apple II. Anyhow, this encapsulated in fancy braces would make it a set, right? It would be the set of A cross B specifically, right? It's basically something that produces ordered pairs, all right? It's unfortunate that there's a lot of symbols that are a lot of commas here, even inside and outside the parentheses, but just convince yourself that, again, it's like an X and a Y and an X and a Y and an X and a Y. Grouped, a collection of them is a set, right? All right. The last one is, well, no, it's not the last one, far from it. I have to draw the diagram, so let me do that now, please. Bear with me, I'm sorry. I have to do this over and over again. Yeah. I drew 2 of these on the page so that you have a reference. This is kind of fading, but let me see. Oh no, yeah. This may be the end of my black marker. Alright, I drew these 2 things adjacent to, boy, that stinks. Hopefully that is visible. I don't know if that's an improvement or not. Let's see. That's a little bit better. But in each of these, the reason that it would be to your benefit to have these 2 things adjacent is that you can refer to the regions in each by Roman numeral. See. And again, there will just be for formality a U tucked in here, because that is referring to universal set, right? As opposed to this unique set A's, B, and C independent. I'll put that there. What is in A only is 1. What is shared between A and B is 2. And what is B only is region 3. What is shared between A and C only is referred to as region 4, and these are Roman numerals. And this is a 5, and this is a 6, and this is a 7, and what is outside everything in general is Roman numeral 8. All right. The reason why, again, I tried to, just draw this a little bit better, have these things next to each other is you have to really fill in the diagram in order to answer the one question that is question 29. Okay. And you always start with the thing that is shared amongst all of them. So if I give you sort of procedures here, what I'll do is I'll write it here and then we'll work it out. I'll put that on again in a moment. Okay. Start with region 5, which is shared by all. Then after that, do region 2, region 4, and then region 6. Oh boy. It's not really that visible. If I hesitate at all, it's because I'm doing too many things at once here. Alright, is that a little better? Suck. Okay. It wouldn't die in the middle of my using it. That's better. There we go. So I'm gonna have to buy another set of markers. All right. What else? Then we do 1, 2, and 3. And that's very hard to see. That's a little bit better. And then the very last thing you do is the thing outside that does not include anything, or is not part of anything else. All right. In the context of the problem that is given here, I'm going to use red just because it writes well. No, I hate doing that. Don't do that. All right. It says, out of 500 people, 270 people listen to hip-hop music, 320 listen to rock music, and 160 listen to country music. All right. The real important information is actually the last sentence. It says 50 people listen to all 3 genres of music. That's always going to be the most important thing. The dead center, region 5, which is the overlap of the 3 circles. Start with planting that number there. All right. So 50 would be in here. All right. It is from that you could do region 2, just above it, region 4, just next to it here, and region 6, which is just to the right of it. That's why you do things in this particular order. 5, 2, 4, 6, and these are Roman numerals. Okay. So in the case of 5, I'll just put this over here to get it out of the way. All right. We're going to use 50 because that was explicitly stated to us. I think I need the light. To figure out 2, let's do this calculation. 2 is going to be brother. What is in No, sorry. Okay. Let me do myself a little favor too. Instead of calling these A's, B's, and C's, I'm going to call A hip-hop, B I'm going to call rock, and C country. Okay. And what I want to do to figure out region 2, that is what goes here, is I'm going to incorporate this 50, all right? But it's going to be some quantity minus 50. The quantity that this happens to be is things that are hip-hop and rock only. So one of the sentences, it says 140 listen to both hip hop and rock. It doesn't use the word only, but it's implying that. Anyhow, the bottom line is that this is really going to be 140 minus 50, which means that this is 90. Okay. Region 4, which would be here, right, is going to be what is hip hop and country only. Minus the same number. Why minus 50? Because 50 is things that would include rock as well. People. All right. So there is a sentence here that says 80 listen to both country and hip hop. I just sort of use those phrases backwards. So this is going to basically be 80 minus 50, which is 30. And I will place the number 30 here. Okay. There's sort of a charming sort of a symbol there. It looks like Celtic knots, right? I think so, anyhow. Region 6, which would be here, is things exclusive to rock and country, apparently. Yeah. So, rock and country only, minus 50 would be this other sentence that says 120 listen to both country and rock. Again, they don't use the word only, but it is implied. So it is 120 minus 50, which is 70. Okay. Region 1 is A only. Right? It itself is just A only, but what is it going to be? It's going to be, let's see. Oh, part of the fragment of sentences at the top in red, it says 270 people listen to hip hop. So if you take the 270 people who listen to hip hop and then subtract out the sum of these people, even though they don't use, again, unfortunately, the word only, to say that 270 people listen to hip hop is to say total people. And then if we want what is only, which is really just region 1, we would have to subtract out this sum of 90, 50, and 30. So I would really need to add those things first, which is 170. 270 minus 170 is 100. So there would be 100 people here. 100 plus 90 plus 50 plus 30 is the 270 people total that like hip-hop music. Region 2 would be the things that are exclusively rock people. And in that case, you look for the fragment that is written in blue. 320 people listen to rock. All right, so that total, 320 minus 90, 50, and 70 in this case. Added first. And in that instance, it would be 220, 210 rather. 320 minus 210 is 110. So that would be there. And one more of that. I'd say 160 people listen to country music. That would be region 3. This is kind of really on the end of the board here, but hopefully you'll see. 160 would be the total green circle minus the sum, which is these regions 30, 50, and 70. That would be 150. 160 minus 150 is just 10. So a 10 would be here. Okay. Now, meanwhile, I leave myself a lot of space. There is also this region on the outside that is a person who apparently does not like music. or a group of people. Region 8, which would be none of these, all right, is going to be the total amount of people surveyed, that's 500, minus the sum of all of this stuff, which is a lot of stuff. All right. It would be the sum of 100 plus 90 plus 110, just going across from left to right here, plus 30, plus 50, plus 70, and then plus 10. And what you would get from that is 460. 500 minus 460 is 40. So 40 people down here. Okay. Now, as much as that is kind of an arduous thing, it's kind of satisfying, right? Especially when it's finished. Now, only having done that, can you actually answer the question, which is why I rigged it so that you have to do that first. Here's what the last thing is for this. 29 says, using the three-set Venn diagram here above, how many people do not listen to country music? People who do not listen, it sounds so terrible. It's like, you people don't listen. All right, people who do not listen to country music, all right, should equal which regions in theory? The picture would make it a little bit easier, right? The people who are outside the green circle that I am stupidly tracing in blue here, what are the regions that are outside this, the trace that I'm drawing here? 1, 2, and 3, and 8. Right, and that means the numbers that represent 1 is 100, 2 is 90, 3 is 110, and then 8 is 40. All right, and total, that would be 340 people. Don't listen to country music at all. Okay. And that is done. I'm going to point at this. All right. The next thing is from chapter 5. There's this table here. All right. I made it so that you could basically, there's a little bit of space to work, not a lot, but you just check off as yes or no. All right, so if it says determine whether 963,888 is divisible by 2, 3, 6, 9, 10, 5, 4, 8, and 7. All right, just because it would, the reason that anybody learns divisibility at all is that it helps when you're trying to simplify a fraction by hand. Because you could use those numbers, the top number and the bottom number divided by the same divisible figure, to reduce a fraction. So you know that something is divisible by 2 if it's even. I need to erase this first. So we got about 2 hours and a half hours. Okay. And this is your original number. 963,888. That's going to drive me nuts. Keep putting it down. And you're testing it out for divisibility here. You can divide nicely, that is, for lack of a more eloquent expression, you can divide by 2 without a remainder. That is what it means to be divisible. You can divide for nearly divide anything by nearly anything else. The only exception is you can't divide by 0, legally speaking. It doesn't work. You could divide by 2 if the number is even. Does it end in an 8? It does. So therefore it's even, and therefore it works with 2. I would do things in this particular order because it's strategic. The sum of the digits. If you added all of these together to form a sum, is the sum divisible by 3? That's really what this is implying. Well, the sum would be what? The sum would be 42. All right? 9 plus 6 is 15. 15 plus 3 is 18. 18 plus 8 is 26. 26 plus 8 is, let's see, 34. 34 plus 8 is 42. And then you get stuck with another number, but you can pull the same trick. All right? Add these two. You get 6. Can you divide 6 by 3 nicely, for lack of a better expression? In other words, if you divided 6 by 3, would you get a remainder of 0, which would be the ideal, nice situation? Yes, right? If the sum is divisible by 3, then the whole number is. Therefore, 3 also works. Okay? The rule for 6 is, do 2 and 3 work? Yes, therefore 6 is a better choice. All right? The rule for 9 is very similar to 3. Can you divide 42 by 9 nicely? Right? You could divide anything by anything, right? Or almost anything by anything. But in the case of 42 divided by 9, you're going to get a remainder. It's not going to be 0. It's not going to terminate, right? As a 0. All right? 42 divided by 9, well, 4 times 9 is 36. If you did this, you'll see what you get. 4 is 36, the difference is 6. You would have 6 over 9, which is really 4 2/3. This is a remainder. So, no good. Doesn't work nicely, the sum, therefore it doesn't divide nicely by 9, it is not divisible by 9. The rule for 10 is, does it end in a 0? No, therefore it doesn't work with 10. And then there's 5. Does it end in a 5, perhaps? No, does not work with 5. The rules that are beyond these, to me, are almost more trouble than they're worth. There's a rule for 4, which is to analyze the last 2 digits, and a rule for 8, which is to analyze the last 3. And then there is technically a rule somewhere out there in the ether for 7, but that to me is completely more trouble than it's worth. It would just, you just divide. It's more work to look for a rule. All right? In the case of 4, you're looking at the last 2 digits. Can you divide 88 by 4 nicely? And that is, there's no remainder, or a remainder of 0 if you like? Yes. All right? Rule for 8. Can you look at the last 3 digits and divide by 8 nicely? Yeah, it'd be 1, 1, and 1. All right, so absolutely. The 7 rule would be to divide this number by 7, and that's just not going to work. All right? If you were to divide 9, 6, 3, 8, 8 by 7, you are not going to get a remainder of 0. It's not going to work in this case, but here's proof of that. Right. 7 goes into 9 once, roughly, with 2 left over. 7 goes into 26, roughly 3 times, with, let's see, 4, 5 left over. 7 goes into 53, roughly 7 times, which is 49. The difference is 4. 7 goes into 48, let's see, 6 times, which is 42. The difference is 6. 7 goes into 68 9 times, which is 63. The difference is 5. 7 goes into 58 8 times, which is 56, and you would get a remainder of 2. All right, not 0. So it's going to be awful. All right. Again, you can get a decimal number. You could write this in the style of a fraction, but it's not divisible because it doesn't just simply terminate nicely. All right. So 2, 3, 6, 9, pardon me, 2, 3, 6, 4, and 8 are what 963,888 is actually divisible by. Right? Okay. Determine the prime factorization of 222. You could use trees, or you could use, for lack of a more eloquent expression, upside down division by prime numbers. I'll do it both ways. So if you have 220, and you have division written in a box oriented like this. In the United States, they tend not to write the box this way. If you go to, I've seen some folks from the islands like Jamaica and Haiti, when they do division, they sort of draw it up, all right? And it produces the same result, so good, all right? It works either way. I'm just calling this upside down because of the orientation of this being like so, rather than like this. All right. Anyhow, if you do factor trees, you consider two things that multiply together to start with that are 220. And maybe the easiest pair would be 10, because there's a 0 in it. And then whatever times 10 would be 220, would be the number 22. All right? And you would proceed in factoring like so until you hit prime numbers. Now, you would need to know that prime numbers are 2, 3, 5, 7, 11, 13, and they go into infinity. They are identified as having two factors each, one and itself. So these are neither of which are prime. They would best be called composite. So you would break down 10 into, say, 2 and 5. Prime, prime, so far so good. And 22 would be 2 and 11. Right? And the written nicely incarnation, the prime factorization of this, would be to use abbreviations, right? How many 2's are there? There's 2 of them, so 2 iterations of 2 is 2 squared. How many 11's are there? 1. How many 5's are there? 5, 1. And in descending order, like so. You can accomplish the same thing with this alternative technique. I can only think to call it by how it actually works out. It's upside down division, from my perspective at least, by prime numbers. So you start with the first prime that is divisible. Remember, divisibility. You could divide anything by almost anything, or vice versa. You could divide anything by almost anything. 0 is the one exception. All right, but not nicely. All right, you might get a remainder. So this is even, works with 2, right? And I'm going to keep proceeding with 2. Continue until it doesn't work. Anymore, all right? And then you're going to stop when the quotient is also prime. Two goes into itself once, 2 goes into itself once, 2 goes into 0, 0. This is not a prime number. Continue with 2 until it doesn't work. Still even, still works with 2. 2 goes into 11, roughly 5, with 1 left over. Read that as 10. 2 goes into 10, 5, 55. This is no longer even, so 2 no longer works. So I'm going to switch up for the next prime number. Next prime number would be 3. Sum of the digits. If the sum of the digits divides nicely by 3, then 55 would as well. Well, 5 plus 5 is 10, and 10 does not divide nicely by 3. It would be irrational. You'd have decimals, a remainder at any rate. So next prime number is 5. So you go with 5. 5 definitely works because it ends in a 5. 5 goes into this once. You stop when the quotient, that's what these are, is also prime. And the junk on the outside here is the prime factorization. The advantage to using prime factorization, so gathering them, identifying them, is that you can use them to identify a greatest common factor, which follows, or a least common multiple, slightly tweaked method. So I'll write that here. Let me try to squeak this in. bought more markers. I know I should have. Next question. This was 31. Here's 32. There's several different ways to identify a greatest common factor and least common multiple. I think the go-to method is more brute force. All right, and I'll do it both ways. All right. When you're trying to identify a GCF versus you're trying to identify an LCM, all right, you could list factors, all right, or you could try prime factorizations. All right. In the case of multiples, you can list multiples, but that would be very cumbersome because they're infinite, whereas factors are finite. Or you could try prime factorizations. I would definitely go with the prime factorization method for least common multiple. For GCF, might stick with listing, because it might be faster. All right. Now, if you're comparing two numbers, in the case of problem 32, what I had suggested was find the GCF for 25 and 35. All right. Here's the list of factors of 25. 1, 5, and 25. It's not too complicated. They would be pairs, technically. 1 times 25 is 25, and 5 times itself. You only write it once. For 35, it would be 1 and 35, and 3 and 7. And as you can see, everything has 1 as a factor. But the, I should have used, sorry, 5, right? In this case, this problem has a greatest common factor of 5. That's the GCF. That's the biggest number in these two lists that they have in common. You could attempt to count by 25. That would be to list these. 25, 50. I sound like I'm at an auction, right? 25, 50, 75, 100, 125. Do I hear 150? And I hate that. And you get to the answer, but it would be, it would take a long time. And in the case of 35, it's a less familiar number for me. So I'd be like, what's the second one? 70. All right, and then the third one is 105. All right, and the next one is 140. And then eventually you get to 107. And, you know, it's problematic doing this is the bottom line. The answer is 175, and I'll just continue with this list of 25s, all right, to show you. It would be cumbersome to identify this LCM by listing, because it might be a really long time before you finally get the match, all right? So what I would suggest to do in this case is to use prime factorizations. It's a little intricate, all right, but it would spare you from having to go through this trouble. All right. And there is a similar way for doing this with GCFs. It's just tweaked slightly. So what I'll do is I'll draw factor trees up here, and perhaps upside down division by primes as well, if you want to explore that option. And then we'll see what we get. We already know what the answer is, right? The GCF is apparently 5 for 25 and 35. The LCM is apparently 175. Yay. All right. If you did factor trees for the sake of getting a prime factorization in either event, here's 25. You would break it up into 5 times 5. Those are prime. And then use an abbreviation. It's 5 squared. In the case of 35, you would break it up into 5 times 7, right? Which is 7 to the first times 5 to the first. Here's how these two methods deviate, right? When you're looking for a GCF, going about the process this way, using prime factorizations, right? You take the higher, the lower power of bases in common only. That's a bit verbose, but that's the case. Now, what do they have in common? They have 5s in common. Those are the bases in common. They don't have 7 in common. You wouldn't even consider it. And then you, somewhat ironically, go with the lower power. What's the lower power? 1. So in this case, 5 to the 1 is just 5, which we got from listing. All right. Again, it may be not that practical when you have a number that's warm, fuzzy, and familiar, like 25 and maybe 35. Because identifying their factors is not that difficult a task, right? When you get a number that's beyond the scope of what is familiar, then you might try this for GCF also. When, I need to erase this and put this back. When you're looking for GCF, I'll put this in black. Pardon me, when you're looking for LCM, least common multiple, you choose the higher, or the highest, as in lowest, power of each unique base. You don't care in common or not, right? Each unique base. They don't have to be in common. You just want to cover all bases, so to speak. So, and you want, somewhat ironically, as I know it says least common multiple, you want the highest power though. Of the 5s, which is the higher, this is starting with the thing that they actually have in common, but it doesn't matter. Which is the higher power? 5 squared. We would go with this, not this. Then we would also consider 7 because we want each unique thing, each unique base, each unique factor. All right, and there's no there's no basis for comparison. There's no other 7, so we're definitely taking that. Anyhow, then we would do the multiplication. 5 squared is really 25. What's 25 times 7? 175. This takes a little bit of getting used to, but it is a powerful method once you got it down pat. All right, in a similar way to the upside down division by primes. You can get the pieces of prime factorizations that way as well. Okay. All right. Moving on. Have to go get another napkin because this is dying out on me too. We're at 3 hours now. Okay. Nearing the end, I swear. I wrote a sort of a reminder on here for rules for integers for adding and subtracting versus those for multiplying and dividing because they get confusing, and especially for kids. It's hard to distinguish what operation is actually going on, right? Because of the abbreviations we use, right? Anyhow, when you're adding or subtracting, if you know that that is the task, right? The adding and subtracting rules for integers is that the combinations decide whether you really add or whether you really subtract. It's annoying. And you may have to make some adjustments first. So, if you have the same signs, whether they're both negative or they're both positive, you actually add. And if you have one of each, one positive, one negative, you actually subtract. Right? And the sign of the answer matches the bigger number, which, to be perfectly correct, it would be better to say the larger magnitude number, even though that's kind of alien. But bigger number, I think you know what I mean when I say that. I just don't want to conflate it with greater or less than. I'm not really using it in that context. Anyhow, in the case of 33, you have something that looks like this. That's the way it would show up in a textbook. In textbooks, because they have trouble writing in superscripts, they don't bother to do it too often, especially older books. They will resort to using a parentheses to isolate a number as an integer. What you might see is something like this. It means the exact same thing. A slightly smaller number and maybe in superscript, but these are the same thing. Anyhow, make one little alteration. If you see a double negative, and it has to be between two numbers, change it. And what does it really change to? It really is this. Situation. And now you would consider the rules for integers as they pertain to an addition and or subtraction problem. What have you got here? You have one of each. So are you going to add really, or are you going to subtract really? You're going to subtract. In which case you're going to get the digit of 1, because that's what happens. And then you take the sign of the larger magnitude. So if the larger magnitude number is really 4, meaning its distance from 0 is greater, right, it's going to be a negative 1. Then in the case of 34, you are given something that looks like this. The same digits, but they're written like this. Right? What type of problem is this? Well, if there's no extra symbol tucked in here, as in this case, this is understood as being a multiplication problem. It really means this. But they go opting for the style of multiplication that is implied or by a parentheses. Anyhow, once you have identified that this is really a multiplication problem, and if in theory it was a division problem, same set of rules, all right, consider what you have. You have the same signs, which does not decide the operation. One of each or both the same decides whether you add or subtract really. In the realm of multiplication or division, it does not decide, hey, now you have to do one or the other. All right, if it's multiplying, it's multiplying. What you start with is what you end with. The only exception to this, perhaps, is for a different reason. All right, if you had division of fractions, you multiply by reciprocal. That has nothing to do with the signs. Anyhow, same signs means that you have a positive answer. And then it's just 4 times 3, which is 12. Subtracting produces a 1. Okay. This is something, again, a little kid, all right? Well, not even a little kid, what am I saying? If you go into elementary education, you're pretty much in the confines of kindergarten through, what, 5th grade in New Jersey? Or perhaps the 6th grade, right? If you work in parochial schools, right, they might stretch that into, it really is middle school or junior high, you might call it, all right, 8th grade. Anyhow, the subject of integers will come up probably around maybe 4th, 5th, or 6th grade, right, for the first time in the United States. So take the time to explain the intricacies of this, because even if it seems, I can figure it out with a calculator, that's nonsense. It's the foundational knowledge. It's worth the time, the investment of time to elucidate it, all right? And hopefully I have. For 35. For 35, it's the process of converting something that is a mixed number into an improper fraction. Okay. And in this case, you're given 2 3/5. All right. I just look at it like this. It's sort of a cyclical sort of process. So let me turn this light off if it's concealing that. You're going to do this. You're going to multiply these two things and then add them to the top. So 2 times 5 is 10. 10 added to 3 is 13. And then you keep the same denominator, 13 over 5. If on the flip side, and I didn't ask you this in this problem, but if you're going the other way, if you want to convert an improper fraction to a mixed number, it's very similar to what I had discussed before when you're converting between decimals and percents. Right? It's just opting for a fraction rather than a decimal. All right? So if you had, it's really the top divided by the bottom. So if you had 13 over 5 here written, usually what they used to do years ago is they would say, hey kid, just draw the box next to the 5, the bottom, because then it's in the appropriate place automatically. Right? And then you can just sort of stop, drop, and roll 3 into the 13 in here. And if you were going to do decimals, you'd put a point and you put zeros. But we're going to stop at that point. We're not going to use decimals. All right, we're going to use remainders. So, how many 5s can you squeeze into 13? 2 approximately, and the difference would be 3. Since we're not going to continue with decimal numbers, we're just going to go, okay, it's 3 as the numerator, and then what you divided by, whatever you divided by, that's the denominator. Okay. Fading, 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 fading. Okay. 36, I love this problem. It's like really enthusiastic. I love you, math. I'm gonna just see me at the end of the semester, just like, wow. Man's lost his mind completely, possibly before. 96. This is an exercise in converting an infinitely repeating decimal, any type, into a fraction. Now, there are some things you can just memorize, like for example, this thing you can convince yourself, well, 0.666 forever, that sounds like the mark of the beast, right? Evil math is 2/3, right? And 3 forever and ever and ever is 1/3. Things like that are good to know by heart, certainly, right? But there is a process, and it really is algebra, right? So if you see something like this, with the ellipse marks, rather than the abbreviation, which would be bar notation. This means that. Take this, and even if it sounds silly, all right, call it n equals that. So grab this thing and go, I'm going to call this n as in a number. You can use lowercase, capitals, whatever you want, and draw the ellipses as well. Okay, we're going to rig the situation strategically to chop off infinity. We need to basically delete infinity out of existence. And in order to accomplish that, I do have to, at the same time, preserve some portion of the original quantity. Right. Now, how I'm going to go about both tasks, preserving some portion of the original quantity and also simultaneously deleting infinity out of existence, is going to take advantage of powers of 10. Okay. Remember, as a side note, the effect of multiplying by 10 moves a decimal once. The effect of multiplying by 100, losing my voice, is that it moves a decimal point twice towards the right, right? And times 1,000 would be thrice, right? That way, okay? So, if I want to preserve some portion of the original number, basically the pattern, right? I should emphasize that. Some portion of this, not just the original number, but this pattern that repeats. Then I need essentially to do this. I need to accomplish moving this decimal over so that I have 6. How would I go about doing that? To move it just once would be to multiply by 10. In the context of this label here, n, that would be the same as saying 10 times n, right? So 10 times n would be 6.666 repeating into infinity. All right, now here's where it gets fun. I'm going to now, with all my power, delete infinity. All right, so how do you do that? Subtraction. I'm going to subtract the original quantity, which would be just, if I wanted to be perfectly technical, 1n. I'll bother to write the 1 now. I'm going to subtract. On this side of this equation that I'm creating, it would be a matter of subtracting 10 minus 1, which would just be 9. N. As alien as that might seem. On this side of the equation is the effect that I'm actually after, which is to systematically delete infinity out of existence. And once I've gotten everything past this decimal point gone, as it would in theory be, the only thing that is left over is that portion of the pattern that I really wanted to keep. And now I can solve it algebraically. How do I justify moving 9 from here to here? Do the opposite of multiplying by 9, and it is understood when two things are pressed together that they're being multiplied. So I would divide by 9 here and divide by 9 here. The 9s would cancel on this side, and then I have the fraction that 0.66 repeating actually equates to. The simplest form of 6 over 9 is really 2/3. How come? Because the GCF, which I would have to divide both of these things by, always be consistent, would be 3. They're both made of the number 3, and that's the best choice, greatest common factor. So this would be a 2 on top, and this would be a 3 on the bottom. 2/3 is 6666666666666 forever and ever and ever and ever and ever. Okay. If you divide 2 by 3, you'd see that, even if you use a calculator. Now, if you had something more complicated than 6 repeating, like 2 digits, you may have to use, times 100 instead of times 10. And if you had, a repeater that starts a couple of digits in, all right, you may have to use either 10 in tandem with 100. And it gets a little bit more complex, but this is the basic idea. You're going to delete infinity, and you're going to try to preserve some portion of the pattern via algebra, which is a blessing as a thought process. Okay. 37. I may need to get an order, so okay. I'm curious what time it is. I've been past 3 hours, probably. And moving on. All right, 37 is asking to use the order of operations, but this is what you give it. I just had trouble writing it, so I was using Microsoft Word when I typed this. So I wrote these things kind of sloppily. I wrote them sideways, using forward slashes rather than the traditional intuitive numerator sitting on the denominator. This is how it really should look. Anyhow, the order of operations would dictate that you divide before you subtract. So even though this is written over here and we tend to read left to right, your focus is really here. And in the case of division, you have to make this adjustment. Keep change flip, which is to preserve, flip as in blip. Keep this fraction exactly as you see it, 14 over 45. Change the operation, somewhat ironically, to multiplication, and compensate by using the reciprocal of this, that is to flip it. The reciprocal of 7 over 9 is 9 over 7. Now, you can brute force do what you need to, which is to do 14 times 9, top times top, and bottom times bottom, but I would advise against that, right? If you know about factors, right, then you could elect a greatest common factor and cross simplify. That would be more strategic. It's not really cross multiplying, people sort of say that. It's cross simplifying. First, right? Not wrong if you did 14 times 9 and 45 times 7, but you're going to get large numbers which are less and less familiar. If you instead recognize that there is a relationship above and below these lines, even though they're diagonal from one another, it doesn't matter, then simplify those numbers by their greatest common factor. They're both made of the number 7. I know it sounds weird to say that 7 is made of itself, but yes, in the context of factors, that is true. So 7 divided by itself would be 1. And 14 divided by 7 would be 2. Simultaneously, there is a relationship between these two numbers, above and below the lines. So it would be to your advantage to cross-simplify those as well. And ideally, you use the greatest common factor. So 9 and 45 are both made of 9. 9 divided by itself is 1. 45 divided by 9 is 5. And now, actually do this. Top times top, bottom times bottom, in which case you would get 2 sitting on top of 5. And you notice that I didn't even worry about this, because I didn't need to. I'm just going to scoot this down. 13 over 15 minus 2/5. Now, the problem with adding and subtracting fractions, which makes them, in theory, harder than multiplying and dividing, is that the denominators must match. Right? Whenever you have to add or subtract, the denominators must match. It's not too hard. There are shortcuts. You could just multiply these two numbers together. You have a common denominator then, and then compensate by changing the numerators in a similar fashion. All right? But it would be more trouble than it's worth. Instead, what you can do, if you know your multiplication tables, which is another reason, not to go off on a tangent, but another reason to encourage your students to memorize information, all right? Again, whoever decided in the position of authority that children should not memorize their multiplication tables was a damn fool, all right? It's hobbling. So if you had that information memorized, not just boop, 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 press a calculator, all right? Then you'll go, strategically, I can upgrade this to something that matches. Namely 15, right? Sorry, not to get ferocious, right? I feel so fervently. All right, so 5 times 3 is 15. If you change the bottom in such a fashion, be consistent. Do the same thing to the top. You can get away with murder in math as long as you are consistent. Whatever you do to the left side of an equation, do to the right side. Whatever you do to the bottom of a fraction, do to the top. That's what makes it legal. This is really 6/15, all right? Which means that the problem in general is really 13 over 15 minus 6 over 15. And once the denominators match, you only add or subtract the numerators. So just pay attention to this. 13 minus 6 is what? 7 over 15 is your answer. There's a lot of intricacy to this. It doesn't seem like too complicated a problem. You got 3 fractions, but it involves a lot of changing. Okay? And again, not to belabor the point, don't ever feel bad about memorizing certain fundamental facts, or nor should you discourage, all right, that process, especially for a little kid. All right? They need to learn how to memorize. They're not geniuses yet. All right? Someday. All right? 38, I just simply told you to use the power rule. I want to refer to a handout that I gave you because I think it's useful. All right, and there's another thing. If you like any of the diagrams that I have made, steal them. I'd be happy and proud if you did. All right. This is a diagram summarizing rules of exponents, of which there are technically this many, 7. But it's these 5 that are very useful. People often confuse these two because they look very similar, because they both involve multiplication somehow. But in the case of the power rule, it's distinguishable by the fact that it is an exponent raised to an exponent, not just sitting next to each other, as in this case. So if you have an exponent raised to an exponent, this is, put that down, 2 to the 4th, and then outside it you see to the 5th. If it's an exponent raised to an exponent, that means that you need to employ the power rule. And the power rule is basically to multiply. Multiply these two things. So what's 4 times 5? 20. Now, you could write this as a standard number, but realize that it would be 20 iterations of 2. 20 clones, and then multiply it. It would be huge. So it is arguably a better answer to leave it concisely written as an exponent. 20. All right. Then there's scientific notation. All right, realize what scientific notation is. It's an abbreviation for either very large or very small quantities. All right, usually things on the scale of, astronomical or, microscopic or nanoscopic even. All right, the irony is because of the system that we have for numbering, decimal system, even something that represents a puny amount can be very, very long, which is why I gave you this problem. 39 is the mass of an electron. An electron, of course, being very tiny, but even in spite of the fact that the quantity, its mass, its kilogram equivalent, would be like this in the standard system, kind of exaggerating the space here on purpose. Even to write it is a nuisance. Hopefully I haven't miffed it. I gotta check. Yeah, that's it. kg, kilograms. This is how you would express the mass of an electron if you wrote it out in our run-of-the-mill standard system of numbering, right? The decimal system. And as you can see, it's kind of impractical because even though it's a really tiny thing, it's still a vastly wide number. So what we have come up with, not me, all right, the community, all right, has come up with is scientific notation, all right, basically an abbreviation for either vast quantities that are on the astronomical scale, right, or on the nanoscopic scale, right, or subdivisible somehow. Anyhow, to convert something to scientific notation has its standards, so just be careful, all right? Something can kind of look like it's in scientific notation, but not technically be, right? To be officially in scientific notation, you can only have one non-zero digit up in the front of a decimal point. If you have 2 digits here, and it's not a 1, if you have 2 digits in the front, that's already a problem, right? All right, that's not scientific notation technically. All right, it has to be one non-zero digit. And then secondly, it has to be, you can't put a 0 in the front. It has to be a non-zero. on the flip side, is to compensate for this vast swath of space by expressing that as a power of 10, you know. Now here's what I would suggest you do. All right. Start out by writing the number that is the non-zero portion of this in this void here. So if it's 911, all right, or 911, put that here to start with and separate it like so. Then count the number of spaces, as arduous as that is, all right, from where you start to just in between these as it is here, all right. A good textbook would have adequate spaces in between sets of 3 zeros, or sets of 3 digits. It doesn't have to be 0 technically, all right, rather than have them all bunched, right? Again, here's another discrepancy between the way that we do math here and say somewhere else. In the United States, we don't put commas on the right side of a decimal point. I'm not sure why, all right? To me, it would make it a little bit more obvious, but we don't do that, right? What we are told to do is leave a void, right? Like so, to make it a little bit easier to read. But textbooks don't do that anyway, right? Not that I've seen. Anyhow, so count, right? Make waves. Count by threes. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, and then I need to go one extra space. So that would be 31, right? Spaces. That would be the equivalent of multiplying by, believe it or not, by 10 to the 31. But there's one other adjustment too. To sort of reserve the conversation of a sign associated with a direction. I don't do that when I'm converting to scientific notation. Personally, what I do is this. I ask myself, is this a small quantity or is this a large quantity? And I understand that that's kind of arbitrary, but hear me out. A small quantity in my own mind anyway is something that is less than 1. A large quantity would be something greater than 1. This is something, as you can see, that is drastically less than 1. Right? So, small quantities, they have a negative exponent. Large quantities have a positive exponent. This is a negative 31. 9.11 times 10 to the negative 31st kilograms is the mass of an electron. Okay. Now the problem that follows is going the other way, really. And in this instance, I would now use a sign to denote a direction that you have to move a decimal point. The reason I don't like to do it the other way is that it can be confusing because they conflict with one another. It depends on what you're starting with and what you're going to. All right. If you're going to a standard ordinary number, all right, some textbooks call that a decimal number, even if it doesn't look like one, and others call it a standard number, which I think is a little bit better, even if it seems kind of funny. The average distance from the Earth to the Sun, right, is this quantity, and this is problem 40. 1.5 times 10 to the 8th kilograms. Not kilograms, ding dong. Kilometers. Kilometers. And here's another discrepancy, again, not to belabor the point again. Our spellings here in the United States, right? Elsewhere would be R-E as opposed to E-R. Okay. Kilometers. 1.5 times 10 to the 8th kilometers is apparently the distance between the center of the Earth and the center of the Sun, on average, because it will change, right? Now, here's what I would suggest you do. You're going to move a decimal place, right? That is represented by this quantity, the effect of, as I stated earlier, the effect of multiplying by 10, all right, which itself is a power of 10. 10 to the first is 10, is to move a decimal place once, right? Times 10 is move once, one place. Times 10 to the second, which is 100 really, is to move twice. Towards the right, right? The truth of the matter is, right, it's the sign that decides, right, in this case. So reserving sign as designating a direction that you move, convince yourself of this much information. If you have a positive, then you're going to move the decimal point towards the right. Right? If you have a negative exponent, you're going to move the decimal to the left, which is that way versus that way. In this case, you happen to have a positive. So you take this quantity, 1.5, and then make waves, right, towards the right. How many? 8, apparently. 1, 2, 3, 4, 5, 6, 7, 8. And just to distinguish it, I'm going to exaggerate that. Why make waves? Because in the voids, you're going to put zeros. Right. So this is fading, so I'm going to use this one. 0, 0, 0, comma. On this side of the decimal point in the United States, we use commas. All right, 0, 0, 0, comma, 0. And then nix this. All right, so what is this as a number, a standard number? 150 million kilometers, right, is the average distance between the sun and the earth. Right? Depending upon the time of year, it would be different, right? Okay, right. Again, positive exponent, move right, negative exponent, move left, decimal point. For 41 is to factor, for the sake of simplifying, a radical. When you have square roots, here we go again. All right. It's probably the water from my eraser making it worse. All right. When you have, say, something like the square root of 20, right? There's lots of different ways that you can present an answer that is arguably simplified for the square root of 20. First of all, it's an irrational number, which means that it is infinitely stretching and has no apparent pattern to it. All right. You could go this way, which is to estimate. All right. Or you could go this way, which is to simplify officially, just to basically reduce the figures involved. Estimating is basically rounding at some point. Right? Now, even if you use your calculator gives you an estimate. I think that is unfortunately making that bad. I hope that's not too dark. Let's see. An estimate by hand is to figure, well, what two perfect squares is 20 in between? It would be in between 16 and 25. So if you're talking about square roots specifically, and this is 4, and this is 5, then this would be somewhere in between those, and you'd say it's about 4.5. That's not correct, but it's close to it. It's an estimate. To simplify is arguably a better choice because it's preserving all of that infinity without having to write all of the infinity. So as part of some other calculation, it really is preferred. And in that case, you're either going to use the product rule, all right, or if you had, say, something written stacked, you would use the quotient rule. The product rule is simply to take the quantity and break it up into 2 pieces, all right? Ideally, all right, the highest perfect square, if you're talking about square roots, possible, and then maybe some leftover, which is sometimes a prime number and sometimes not. Sometimes it's a composite like 6 that is just inconvenient to factor further. So in the case of 20, considering all the factors of 20, and there are quite a few, right? Everything has the perfect square that is the number 1, but that's not the highest perfect square, and you want ideally the highest, which is 4, right? The leftover would be 5. The advantage to strategically choosing the highest perfect square possible is that at least some portion of this original quantity will leave the radical. What's the square root of 4? 2. That means that this is equal exactly, even if it doesn't seem that great, to 2 square root of 5. That's a better answer than, believe it or not, saying 4.5. Even though 4.5 is a decimal and that's probably more human, right? This preserves all of infinity while using smaller figures, right? 4 hours. For 42, you have this. You're trying to subtract these. 5 square root of 3 minus 12 square root of 12. When you're trying to add or subtract radicals, which is what you would call anything with this sort of square root hat on it, if you will, you have to meet certain criteria. They have to be the same index, which is the type of radical. They're both square roots. And they have to have the same radicands. That's the guts, the inside. Right? The index is the type. All right? This is the insides. Now these are both square roots because there's no number written there. It would be a 2, but math people don't write that. For the same reason they don't always write 1 or decimal points or positive signs. It's the OG. It's the original concept. So like the only way they distinguish this from another type of radical would be like putting a 3 here for cube root. Anyhow, these clearly don't match even though they are the same index. So we're going to factor this. And again, ideally, the highest perfect square possible, and then some leftover. Think of the factors of 12, of which there are many. Everything has 1, but we want the highest perfect square. The best choice would be 4. Again, just coincidentally. And then what causes that? 4 times 3. According to the product rule, that's what that is. This will become 2 square root of 3. So now we can subtract. And once you have the situation arranged, you only add or subtract the coefficient, the outsides. That which is sitting in the front of the radical. So what's 5 minus 2? 3, and what is that sort of, if you think of it as like a variable, square root of 3. So it's 3 square root of 3. Getting a carpal tunnel here. All right. 43 is super easy, right? Well, that was 42, yes. That was 41. It's asking you to identify properties. The three that are important are associative, commutative especially, and distributive if you do any sort of algebra realistically. I've noticed that in recent years, the distributive property gets used a lot more in grammar school math than it had. Right? And the reason for that is that we're trying to train children to think that, listen, if something is difficult to add or subtract directly, pardon me, usually adding, then maybe you could break it up into pieces. All right, that's really the point. And distributive property is more practical in the context of algebra, I would say. Not to corrupt your opinion, but that's how I feel about it. All right, and here's an example of that. This is an example of the distributive property to answer the question. Why is that? In algebra, when you can't really perform the operation because you don't know what the letter is, you could at least distribute the outside content and it would be legally correct. This is the distributive property. If you knew what the numbers were instead, I'm not going to be too creative here. According to the distributive property, doing this first, which would be to produce 4, and then multiply by 2 to get 8, will give you the same answer as doing these two things distributed, which is 2 and 6. And this is, pardon me, I'm double talking here. This is really an algebra problem because it's a variable. This is really an arithmetic problem because it is numbers exclusively. But in algebra, you do this because you can't do anything else. In arithmetic, it's an option, right? If it's a convenience for a person to do the arithmetic this way, or to do the arithmetic this way, then legally you can. That's what the distributive property is saying. Now, what follows this is the newfangled stuff from chapter 9. I wrote a little circle here of explanation, right, to clarify that because it's an alien concept. All right. Basically, a mathematical system is the coupling, or the way I put it is the marriage of a set, so you'll see something in fancy braces, and a binary operation. A binary operation is just an operation that involves two parts. Right, 2 factors or 2 terms, technically, if you want to be precise. All right, what it usually means is that you're going to be adding stuff or you're going to be multiplying stuff. All right. Now, I made a table here to sort of walk yourself through the question. All right, and again, it's just a check of yes or no. I said check the group criteria. Right. Well, let me finish reading with purple here. A group is a more specific example of a system. All right, again, a system is, maybe I'm just sorry, I'm being lazy. All right, a system is the pairing together of a bunch of numbers, all right, a set, if you will, and a binary operation, which is usually multiplying or adding. If you have these two things together in tandem, you have a system. All right? A more specific type of system is a group. All right? A group has to meet 4 criteria, though. All right? A group has to be one, it has to be closed. Warrants explanation in and of itself. That has to be include an identity element, which varies. there has to be inverses for each, I should say include as well. Damn it, I can't spell today. And then it has to be associative. And the associative property is considering three things in tandem and grouping two and performing the operation on those two first, and then in the alternate situation, grouping a different set of two. If we were talking about addition, it would be written like this: ABC, ABC, and this is really bad because I don't have a board here. Here, ABC, ABC, easy as 1, 2, 3. Do, re, mi, ABC. Okay. If you grouped these two together on this side, you legally could do them first. If you grouped these two together on this side, you could do those two first. You would get the same answer grouping these two versus grouping these two. That's the associative property of addition, all right? And there is similarly one of multiplication. All right, anyhow, what does it mean to be closed? All right. To be closed means that if you perform the operation, it would only produce more of the same type of thing. More of the same elements. Okay, so the example that I had given you is, as far as a set is concerned, is I gave you the set that is the natural numbers to deal with. All right, remember, the natural numbers are the numbers that are intuitive to us, because when we first learn to count, it is usually on our hands, right? And there's no zero, right? It starts with 1. Right? So here's the set of natural numbers, right? Starting with 1, 2, 3, 4, and it goes on into infinity. Can't list them all because they are infinite. All right? And the binary operation that they gave you was a so-called under multiplication. Okay. Now here's to check the criteria. All right. I left a little space for you. All right, up here in the table to write the set. Just write a couple of digits to get you going. All right. 1, 2, 3, 4. Bunch of ellipses. All right. Let's check to see if it's closed, all right? If the operation is multiplication, if I were to multiply any pair of the elements here, it doesn't matter if it's 1 and 2, 2 and 5, 3 and 1, in any order, right? Would performing multiplication only result in producing another element that in theory would be part of this set? I didn't write every element in this set because it's infinite, but if you think about it, multiplying 1 times 2 is only going to give you 2, right? Multiplying 2 times 3 is only going to give you 6, which is indeed another element in here, whether I wrote it or not, all right? Any combination, any pair of these elements, an element times an element, is going to produce more of these. So therefore, is the set of natural numbers under multiplication closed? Yes, you would put a check mark for that. So far, so good. Okay. The next thing is that, does it include the identity element that is appropriate? Because it can vary, all right? Let's discuss identity elements. There's the identity property of addition, and then there's the identity property of multiplication. any number plus 0 is equal to that number. Any number times 1 is equal to that number. A is in N. Right? That makes it more visible or not? I don't think it does. Anyhow, in the case of addition, the identity element is 0 for adding, right? In the case of multiplication, the identity element is 1. So the question realistically is, in this particular problem, is the identity element included as part of the set of natural numbers? It's the very first one, as a matter of fact. All right? So therefore, yes, it includes the identity element. That is appropriate. Yay, we're doing good. All right. Next thing is the inverse elements. All right. I will erase this because I need the space. When it comes to inverse elements, again, insofar as addition and subtraction is concerned, let me use red. All right. There are inverses and inverse property as well. All right, again, of addition versus multiplication. The inverse property of addition is that if you have anything and then you combine it with the exact opposite sign incarnation, that would produce 0. Okay? Inverses produce the identity element, you might say. Simultaneously, the inverse property of multiplication is not a change in sign, but a reciprocal. And that would produce 1, right? Inverses, when multiplied, produce the identity element 1. Now, what this is saying in a very subtle way is that are the inverse elements that are appropriate to multiplication included in this set? In other words, if we have to have reciprocals, are there any fractions listed here? Would it even be possible to list fractions in natural numbers? No. All right. So already we hit a brick wall. All right. All right. The inverse elements, the fraction needed to produce an inverse here for 2 would be 1/2. Right. All right. The inverse necessary, that is the fraction that would produce 1 for 3, would be 1/3. And fractions are automatically not included in the natural numbers because the natural numbers are just the things that you can count with your hands, right? The digits 1, 2, 3, 4 into infinity. No fractions. So we didn't meet the 4 criteria. Right? We hit already a stumbling block. I already took it for granted that it is in fact associative. You don't have to go looking for that. You would, in theory, and it would be impossible, have to check the associative property for every set of 3 things. Right? And you'd be doing that forever. All right? So normally what they ask you is, just try 1 or 2. But that's not really cool. All right? So it usually is just given to you. There is no counterexample, all right, to say, oh yeah, I can't think of one. So anyhow, to answer the question, is this particular system of a set of natural numbers and the operation that happens to be multiplication in this case a group? It's not a group. The answer is no, it's not a group. No! Okay. Moving on, all right? The next question, this is from section 9.2, is clock 12 arithmetic. I've included the table. This is just an exercise in how well could you read the table. It would have, if you were trying to identify clock 12 arithmetic as being a group, you would have to meet the same criteria. But if something is given to you in the style of a table, there are little tricks that you can perform to not have to, do too much work. You just need to know how to read the table, is the bottom line. so on the sheet, I have given you this table. I'll teach you how to read it again. If you want to see, in the case of problem 45, right, whether clock 12, meaning it has 12 increments, right, arithmetic, and it is, in this case, it's addition, right? This is the set. If it's a group, and then specifically an abelian group, that's an even more specific case. Abelians are also commutative in addition to associative. So you would again have to explore the commutative property for each thing in theory. Because commutative property would be, you could add things in this arrangement, you could add them in this arrangement, and they would produce the same result. The order doesn't matter. All right? Is it a group? Is it an abelian group? This has 4 criteria. This has a 5th criteria. So that's why I put, you notice, associative. I put a check mark already. Assume that it is, right? There's a trick when reading the table for deciding whether it is commutative without having to go through the actual work. All right, now, is the set closed under the operation of addition? Since it is, the way that you can deal with that is that look at the table, all right? If you look at the table, all right, and at the same time you consider the elements of clock 12 arithmetic, these are the elements. Is there anything in the table other or in addition to these? Anything in the table that isn't an element? And these would be all of the elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the elements of clock 12. All right. Do you see a 13 in here? Do you see a negative? Do you see a club symbol? Nothing. No. So since there is nothing in this table other than 1 through 12, all right, then you would say, yes, this is a closed set. So good. Without having, all right, to have to, you know, try any sort of arithmetic in the process. All right. And it would be kind of tricky, right? The whole thing was age of 12. Right. Well, in that case, not too bad, right? Number 2. Yeah. I can't tell if it's the marker or the eraser. Right. 2 is a little bit better. Get rid of this. Right. Is the proper identity element, right, included? We're not sure which one of these immediately is the identity element. So what you would do is you would look in the table. There's a trick for identifying it without having to perform any operation or, you know, struggle with it. All right. Basically, there along the side of the table, there are what you might call row headings. All right, the labels. And along this side of the table, there are column headings. Now what you can do is sort of shift the column headings down into the actual table and simultaneously shift the row headings left to right into the table and see where they cross, right? That there's an overlap of these two things in a certain place, right? Look for the cross, the point of intersection in the table. It's a little hard to see in this case because it's not like in the center. What ends up happening, and I'll draw it in a different color here, is that what are the column headings can be found at the very bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And simultaneously, the row headings that would be here are on this far side here. Going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And where they overlap is right on the corner. That means that there is an identity element. This is the identity element where they cross, the point of intersection. All right. Is 12 included in this set? All right. Yes. All right. 12 is included because that is what the identity element is, apparently. Okay. Next. Let me move this. Let's see, next thing is, are the inverses available? Are the inverses included in the set? There's a diagonal line that basically would indicate that you have some inverses at play. But one thing that you could take into consideration is this. All right? If you are not sure, all right, the more involved method for proving point 3 is that there are inverses, is that there's a relationship between them. All right? If we're talking about addition here, all right, under normal circumstances, normally, regular arithmetic, all right, you have a number plus its inverse equals 0. These are an element and its inverse, and this would be its identity element. Combining these by the operation of addition, an element and its inverse would produce the identity element. Under ordinary circumstances, it's 0. What would happen unique to this problem, would be that you have any one of these 1 through 12 identity elements, and then 12 is the, you would have 1 through 12, any of these elements, right? But you're not sure which is the inverses, right? Unless you have another table. But you do know what the identity element is, right? So if you examine the number 1, all right, what combined with 1 would actually be 12? 11. That's the inverse in this case, right? It's not a negative. That would be what would have to be under normal circumstances. But unique to Clark 12 arithmetic, it's a regular, ordinary, positive number, if you will. All right? If you wanted to consider, you know, a random number, let's just say 4. 4 plus what would be 12? It would be 8. These are inverses of each other in the context of this problem. All right? So you could systematically check each pair, all right, and see. But the cheat is to look for the number 12 as a diagonal line. I illustrated it here. There's a number 12 that runs all the way across this from here to here, all right? And if you try to pair, basically, the column headings and the, the row headings, you'll see what the inverses are. 1 and 11 are this 12. 2 and 10 are this 12. 3 and 9 are this 12. All right, that's intuitive, right? Regular arithmetic anyhow. All right, but the point is there is a diagonal line here, all right, that is the identity element only, all right? So that's a way of telling that there are, in fact, inverses. So do we meet the criteria of there being, of number 3, that there are inverses included? Yes, because it's just these numbers in pairs. All right. All right. Now, I took it for granted, all right,
that if you tested out any of these numbers, yes, they would produce the same number on both sides of the associative property. So you don't have to worry about that. I put a check mark there. Is it commutative? If it was commutative, you'd have to test out pairs of these numbers and see if they produce the same results, but it would be tedious to have to do this the number of times for the number of elements that you have. So the trick of reading the graph is to look instead for the main diagonal. And in that case, on this, I drew this dashed line in purple here. From the upper left, the top left, to the lower right. I drew this dashed line. And what you will notice is that there is a strange kind of symmetry here. On this side of the line, there's a 2. All right. Pardon me, maybe I should draw it into the thing here. It's 3 and 3, and 4 and 4 and 4, and 5 and 5 and 5, and 6 and 6 and 6 and 6, and 7, 7, 7, 7, 8, 8, 8. It's like a mirror, you know, there's symmetry. All right. If that line exists, and it has to be from the top left to the lower right in this case, then it is commutative. So we passed all 5 criteria in this case. So therefore, the question is clock 12 arithmetic under the operation of addition abelian? It is. Yes, right? It is an abelian group. Okay. The next thing is a little bit alien too. All right, modular arithmetic. All right, there's ordinary arithmetic that we all understand, right? That especially at this age that we are, right? That if you add numbers, it produces a certain result. Modular arithmetic is toying with that, and that's why it's perhaps a little off-putting, right? And I'm not sure why the praxis examination would include this, because it doesn't seem like the kind of thing that you would teach children that are in grammar school, but hey, whatever. Anybody can understand anything. It's just a matter of time, right? Anyhow, to summarize, modular M is the modulus, is a number. Consists of a set of elements and a binary operation, right? But the number of elements is designated M. So to summarize, mod M, a mod M system is again a system. Therefore, it is a set and an operation. Binary operation. This M, which is known as the modulus, right? And I think this may have come from Italian because it says modulo, modulo. I think I may have spelled that wrong. I gotta check that. All right, is the number of elements. In the set. What would normally be called N is called M. Okay. Anyhow, the difference between this stuff and the stuff that was discussed first, the natural numbers, is that natural numbers are infinite. Modular systems are limited by a certain number of elements. They are finite. And because they are finite, in order to express some quantity that is beyond their boundary, all right, it's cyclical, which means that we would have to interpret larger quantities in terms of the finite elements only. That's why the arithmetic is very strange, right? Like under normal circumstances, 2 plus 2 is 4. But if you have a certain modular system that is shorter than that, right? Which would be hard to think of off the top of my head, all right? May not produce that result. It really depends on the number of elements, right? Anyhow, because these are finite systems, i.e. they have limited elements, they are cyclical in nature and therefore would require that we express larger quantities, that is something beyond their scope, all right, in terms of the established elements only. This is known as congruence. It's kind of explaining, well, it is essentially explaining what equals what using this system as opposed to what we normally do, right? It's like developing a code, if you will, all right? Anyhow, for problem 46, it says, in a modular 8 system, the set would consist of these things. 0, 1, 2, 3, 4, 5, 6, 7. I know that it is called mod 8, but the fact is that the last number is always going to be m minus 1. And it's always going to start with 0, okay? That's why it only runs from 0 to 7. Notice it's finite though, it doesn't go beyond that, or in the other direction either. So if I had a number like 11, I would have to interpret it in terms of these numbers, and you can do that infinitely. The trick to it is this, all right? Right? If you divide any number, including any of these, by the modulus, right? This will produce a remainder. Sometimes the remainder is 0 and we don't really think about it really. Right? When the remainder is 0, we just go, all right, it doesn't have a remainder then. But think about it as having a remainder of 0 in this context. Right? Right? Numbers with the same remainder are congruent. And the symbol for congruence is, at least in this context, is 3 lines, sort of like a super equals, if you will. Again, the purpose of this is to interpret something beyond the scope of the last number here in terms of one of these, because it's cyclical in nature. You can't stretch beyond this. It's like a clock, all right? You could have a clock in theory that doesn't have 12 hours. You can have a clock that is, 7 hours, right? Even when you have 12, right? If you took the number 13, right, what is that in reference to a clock, a regular ordinary 12-hour clock? It's 1 o'clock, right? So that is to say that 1 is equal to 13, or congruent, right? Anyhow, let's do this problem very quickly, having gone through that. Right. If dividing basically by the modulus number, that is the number of contents, any number produces a remainder, numbers with the same remainder are congruent, right? What that means is this. If I took any of these, it might seem a little goofy, right? But let's say that you divided 0 by 8. That's perfectly legal, right? 8 does not fit into 0, it's too small, so you would put a 0, and then you would subtract, right? Oh, wait, something backwards here. Pardon me, I'm putting the wrong number there. These two things multiply is 0, right? And you get 0, and that's the remainder. It sounds silly to say that, right? That the 0 has a remainder of 0, but you could, right? In a similar way, if I did 3, all right, I took the element 3 and divided by 8, how many 8s can you squeeze into 3? 0, they wouldn't fit. But if you're going to do the subtraction, it would be these two things multiplied, and then subtracted here, which would be 0, and in this instance, you would have a 3. The remainder would be 3, okay? Now, You could do this for all of them, but you don't have to. In the problem here, if you're given 60, all right, which is well beyond the scope of 7, if I were to divide this by the modulus number, 8, let's see what the remainder is. How many 8s can you fit into 60? You definitely can, right? 7 whole 8s. Is that visible? Good. And then you would multiply these two and you would subtract 56. And the difference would be what? What's 60 minus 56? 4, right? If you're not doing more sophisticated math, that would be making a fraction perhaps, or decimal fraction division, you would just simply stop here and say this is a remainder 4. What that means essentially is that 60 is congruent to 4. The quantity of 60 can be interpreted using this scale or this system of numbers as being the number 4, right? How come? Because I didn't bother to do it over here. If I were to do this, divide the element 4 by 8, it would still be 0, as it had been in the other two examples. And yes, I would still multiply this and subtract 0. But in this context, the remainder would be 4. 60 is essentially 4, right? In this system. That's the goofy way you would say it. Rather than that, 60 is congruent to 4 in a mod 8 system. That's the answer, right? We've interpreted the number 60 in terms of the elements here. It would be 4. Okay. All right, almost done. The rest are all probability formulas. And we are at the nearly 4.5 hour mark here. Okay. Let's see if I can get this done in less than 15 minutes. I don't know. I don't want to skip, be shortchanging anybody. That's why I'm taking my time. Let's see. All right. 47 to 52, it's just probability stuff. All right. So you would basically need formulas for these. Right? In the case of 47, it's asking for a theoretical probability. Theoretical probability is this formula. The top number is the number of outcomes favorable to the event that is specified. The bottom number is the total number of outcomes in the sample space, or in the set, you could say. These are synonymous. Okay. So, in the context of problem 47, it says, calculate the theoretical probability of rolling an even on a 6-sided die. All right. If it helps, I'll just write even in here and even in here. All right. And then consider the sample space. A 6-sided die would have these labels. 1, 2, 3, 4, 5, 6. All right. How many of these are there total? 6. How many of them are even? 2, 4, and 6 are even. That's 3. 3 out of 6, simplified, is a half. You could say it's 50%, but a half is sufficient. Right. 48. All right. 48 is calculate the odds in favor. All right. This is a different formula. odds in favor is a little different from probability. Odds in favor is, it's really for the purpose of gambling, to decide how much you're getting paid as a result of winning. Odds in favor is this formula, A over B. This is number of favorable outcomes and this is the number of unfavorable outcomes. So even if you did the same problem as before, you would not get the same fraction. Right. In the context, not to digress, but the problem, if you had done it before from the perspective of odds instead, it would be 3 on top, because that's the number of favorable outcomes no matter what. But it would be 3 on the bottom as well. And your fraction would be 1 over 1, right, which is just 1. Anyhow, if you're you're drawing a queen at random. Queen from a deck of 52 playing cards, right? How many queens are there in a deck of 52 playing cards? There are 4 queens. Now, if it was probability, you would simply put the number 52 here. But because it's not the same thing, it's not the total number of cards, it really is this. It's 52 minus 4, all right? That's how many things that are not the queens, all right? There's 52 cards total, 4 of them are queens. How many are not queens? 48. So the odds in favor are 4 to 48, which is better. You could write it as a fraction, 1 over 12 simplified, but it would be better just to distinguish odds from probability. So you might see it written with a colon instead. Even though they mean the same thing, it's just a different symbol would be better. Okay. All right. 49. I don't think this is gonna write. I'm gonna try. One of these might work. It's okay. Try this blue. Okay, for 40. Is it 49? Yeah. Calculate the expected value, which is a sort of average of good things and bad things, good probabilities and bad probabilities, and how they are affected by different weights of value. This is the formula that you would need for problem 49. Expected value, let's call it E, is the first probability times the first amount, right? Plus the second probability times the second conditional amount. And you could do this into infinity if necessary. That's what that extra term is. In the context of this problem, it is most concise to say, okay, what's the probability that is good for me, right? And what is the probability that is bad for me, right? In the context of this problem, it says on a multiple choice test, there are 4 choices, all right? The instructions indicate that 2 points will be awarded for each correct response, whereas a half a point will be lost or deducted for an incorrect response. And then it says that there is no points added or subtracted if the answer is left blank. So what's going on here is that you're going to have 2 different probabilities, all right? If you calculate the first probability, that is that you guess correctly, all right? What would it be? It would be 1 out of 4 choices, which is not great individually, right? But the reward of that is actually more significant. It's more powerful, right? So let's just say hypothetically you did exactly that. You guessed correctly. It would be 1 out of 4, 25% chance for each individual question. You will get 2 points for that. This is points. And this is points. All right. In the context of the second situation here, what would be arguably bad is that, okay, what's the probability of guessing incorrectly? The probability of guessing incorrectly is more likely, really, right? Because there's 3 wrong answers, right, out of 4. All right. However, what's interesting about this is that there's less punishment, right, if you will, right? If you guess correctly, which is a little less likely, you'll get more points for it, all right? In the context of this problem, they describe it like so. They say, well, you're going to lose a point. So it's minus a half a point, right? And then in theory, a third situation, they say that you're neither rewarded nor punished. So whatever the probability would be, right, regardless, it would be times 0. You really don't even have to consider the third situation, all right? What you will have to do, though, is straighten up the arithmetic here, all right? 2 over 4 is what you would get in this situation. This would be a negative, so I'm going to end up subtracting, and it would be 3 over 8. Remember, when you add and subtract fractions, the denominators have to match, so you really have to upgrade this into so many eighths, right? 4 times 2 is 8, so 2 times 2 is 4. And then it is really 4 minus 3 over 8, which means that the expected value is still a positive. It's not very likely, all right? But in the long run, it is actually to your advantage. All right? And the reason stems from the fact that the rewards for guessing, all right, correctly are greater than the punishment for guessing incorrectly. So it is an advantage. All right. For 50, it says, calculate the total possible outcomes, the sample points for 2 consecutive probability experiments. A coin toss and a card, rolling a die in this case. Right? Use either tree diagrams or the counting principle. For 50, these are consecutive events. Just to distinguish them from any other situation. A coin toss and a die roll. I don't know why I'm going to keep pulling the cards. If you did factor trees, you could accomplish the same thing. But there is something that would, expedite this, which is called the counting principle. It's a formula. The counting principle is abbreviated as m times n, right? This is the number of distinct outcomes for the first experiment or game or whatever have you. And this is the number of distinct outcomes for the second experiment or game or what have you. In math world, experiments are games. There's no difference. My hand is being hurt. Okay. Anyhow, in a coin toss, it's either heads or tails. All right. So how many outcomes are there? There's 2. All right. in a die roll, at least if it's a six-sided die, these are the outcomes. There are 6. That means that the total sample points, which is the total number of outcomes, in the so-called sample space, I shouldn't say so-called, it is what it is. Sample points of the individual thing, sample space is the whole set, right, is 12, right? And that's the answer. If you did factor trees, you'd have to basically draw something like this. You'd have the game, the two games, considered in tandem, or one after the other, I should say. And the first one is heads or tails, right? And then let's say you get a head, and then you roll a die. You could get a 1, you could get a 2, you could get a 3, a 4, a 5, or a 6. And in the case of tails, you can get a 1, you can get a 2, you can get a 3, a 4, a 5, or a 6. Right? The end result of H and then 1 is the first sample point. H and then 2. H and then 3. H and then 4. H and then 5. H and then 6. T and then 1. T and then 2. T and then 3. T and then 4. T and then 5. And then T and then 6. These are all the sample points individually. They are the sample space collectively. Anyhow, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Right? Being able to draw the picture is helpful, but the bigger this number is, the more tedious it is. Two more, and I'm already over 4:30. Oh boy. This is why it hurts, because I have to rub so hard to get the blue out. Alright. 52. Calculate the probability of getting an A at random, given that you get a grade higher than D. Alright. This is, no, I'm skipping, I'm sorry. 51. The probability of drawing a heart or a face card from a standard deck of 52 playing cards. This is an example of compound probability. Right? In the case of compound probability, there are the addition rules and there are the multiplication rules. Right? In the case of addition, you need to consider something, whether the events are mutually exclusive or not. In the case of multiplication, you would need to consider things like dependent or independent. That would decide formulas. This was a handout from a while ago. Let me just point to it if you're curious. Here, there's a table that looks like this that summarizes the different formulas. Let's see. I hope that's not, that's a little faint. Okay. In the context of this problem, right, the way that you would decide whether you're going with the addition rules or the multiplication rules is, I'll point to this again, I really should have closed it, but okay. These phrases, or and, in this case. Okay. The addition set of rules are or problems, and again, this, you need to consider whether the events are mutually exclusive or not mutually exclusive. So since it was the probability, the probability of drawing a heart or a face card, are the events mutually exclusive or aren't they mutually exclusive? Things that are mutually exclusive can't occur simultaneously. These can, if they are not mutually exclusive. Can a card be both a heart and a face? They can. Queen could be a heart, queen of hearts, and it has a face because it's queen. All right. So, all right, the formula that we would go through is this one for not mutually exclusive. Probability of two events, all right, the first plus the second. Oh wait, I'm pointing, I'm sorry. It's this formula, because a card can, get inside, if something can occur simultaneously, and in this case they certainly can be the same card, then we need the other formula. That's this. The probability of drawing a heart or a face is equal to the probability of a heart plus the probability of a face. And then you would have to subtract out the situation where they do overlap. The context of "and" in this case is not the context here of "and" for multiplication, because those are consecutive events. Alright. This is the context of conditional probability. And they are basically an intersection in which basically we care about whether they overlap somehow, like in Venn diagrams. Anyhow, here's how we would calculate this. In a standard deck of 52 playing cards, how many cards are hearts? 13 out of 52. In a standard deck of 52 playing cards, how many cards are faces in general? There's 3 faces that are hearts, there are 3 faces that are clubs, 3 faces that are diamonds, and 3, I wish I had a fourth arm, 3 faces that are spades. So that's 12 out of the same 52. Let's consider, they'll be counted twice if we don't subtract, the situation where there's some kind of an overlap, the conditional context, as opposed to the consecutive context, which would be the formulas here. Things that are simultaneously hearts and faces, there's 3. There's the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So we will subtract 3 out of 52. All right. We would add these two first, which would mean 25. And then we would subtract this, minus 3, which would be 22 out of 52. And if you simplify, divide both of these by 2, it would be 11 out of 26. All right, is the probability. All right, which if you made it as a percentage would be something like 42%, if you're curious. Under 50% is not something I would gamble on personally, but that's me. All right, and finally, the last question is conditional probability, which is a different formula, basically. calculate the probability of getting an A given at random, that you get a grade of D. I should have added one thing. I apologize. I should have said, assume that this is the set of grades. A, B, C, D, F. Okay? Nothing else. All right? You could put incomplete in theory. Wouldn't matter, but no A minus, B pluses, nothing like that. Just a standard letter grade. If we're talking about conditional probability, conditional probability is that word and has a different context. The and is not implying that one thing follows another, necessarily. It means we're talking about the intersection. Things that are simultaneous. There's an overlap. All right. And the formula would look like this. The best formula, in my opinion, looks like this. The probability of two events that we're talking about will use subscripts. And just not to confuse this with anything else, we'll use, rather than use the word and, we'll use the intersection symbol. I'm going to try to, for my own purposes, I would reserve the word and for the compound probability and. E1, okay. The hard part of a problem like this is deciding, well, which is E1 and which is E2, and it does technically matter, because you've got to fill in the formula in a certain way. All right. The more specific event I would designate as E2, right, when given two things. What we have here is a grade of A, all right, and if you consider that as a set, there's only one thing, it's A, all right, and then a grade greater than D, which in this case would be A, B, and C, right, using this as the universal set. Okay, of these two things, which is evidently more specific? A grade greater than D could be any one of three things. So this is a little bit more vague, all right? Another way of telling is if we'll look for what follows the word given in the sentence, all right? Let's see. Let's see. What follows the word given in a sentence, that will be E1. All right. What is more specific? That will be E2. So, given a grade is greater than D, let's make that E1. Okay. I'm going to try to squeak it in here. Let's figure out what the bottom is here first. What are the number of outcomes for E1? There's three, right? A, B, C, those three things, right? What's the number of outcomes, all right, that is the intersection of E1 and E2, all right? In other words, what is in common between E1 and E2? This would be the intersection. This is what they have in common. How many things is that? It's just one thing. This is just one. That means that the probability here is 1 out of 3. Okay. All right. that's it. This is a very long video. It's going to take forever to upload. Anyhow, that's how you would do any of the problems on this would-be final exam. All right. I'll take the opportunity to say thank you for listening. All right. I'm sorry I couldn't say goodbye to you in person. All right. And I hope that you're well. All right. I'm going to probably correct your Canvas gradebook now, and then tomorrow I'll update your official letter grade in WebAdvisor. Okay? Be safe out there, and hopefully I'll see you at some point in the future. Okay?